Thank you for joining me tonight, Stephen. It's a great honor to talk to you about your life and your work. You've been a pioneer in computational science from your early work in cellular automata to a new kind of science, and then finally, most recently, the Wolfram Physics Project. And the thing that's most interesting to me about it, having read your book, having followed the Wolfram Physics Project, is back when you started, you were a physicist, you got your graduate degree in physics, and then you kind of you took this other path with computation, and you kind of started studying physics through computation, if you will. And what sort of led you down that path? Because after reading your book, I think that's probably a pretty interesting question to have answered from you.
Fair enough. Yeah. So, this is a bit of a long, shaggy story of my life, so to speak. Bit of framing. I grew up in England. I was, in sort of 1960s to early 1970s, kind of, space was the big thing of the future at that time, as it is again today, but there was a 50-year gap. I sort of followed every spacecraft, all that kind of thing. That got me interested in physics by the time I was like 11 or 12 years old. And I was reading college physics textbooks and so on. Then about age 14 or so, the big thing in physics at the time was particle physics. A lot of discoveries being made. It was kind of, it was the machine learning of that time, so to speak. It was the big, or maybe the crypto of that time. It was the kind of the place where sort of exciting things were happening, bright people were doing interesting stuff, and so on. And I got involved in that. And it was sort of a thing where I think I kind of decided very early that I was interested in I want to solve problems that haven't been solved before. Maybe it's a piece of egotism that I'm more interested in doing things where I feel like I'm being unique and doing something that hasn't been done by zillions of people before as an exercise in a book or whatever else. But I kind of started like, okay, I'm going to think about these things that are on the front lines of physics as it was at that time. Well, I had one important kind of secret weapon, which in retrospect, at the time, I just couldn't understand why other people didn't pursue, which was computers. And so I kind of first had access to a computer around 1972 when I was 12 years old. It was a big computer the size of a desk programmed with paper tape. It had 8 kilowords of 18-bit memory. So it was a weird creature. It's an actual ferrite core memory and things like this.
Oh, wow.
But it was, so, I started using that to try and do little things in physics. They didn't work so well on that computer. But by the mid-1970s, I had kind of started using computers to do things like algebraic computation. So when you do physics, one of the really, the pain points is you have to do all this algebra, et cetera, et cetera, et cetera. I was I don't think I was terribly good at it, but I certainly didn't like doing it. And so I thought, it's boring, mechanical, let's delegate it to a computer. So I did. And at the time, there were various experimental systems that people had built for doing kind of algebraic computation. And I started using pretty much all of them and started actually doing physics computations that way. And that gave me a big boost, I think, in doing things like particle physics. I worked on cosmology. And I was doing it both the physics side of it, and I was using computers to do that physics. And it worked pretty well. And it's kind of cool that papers one wrote when one was 17 years old still get used today and so on. And that's, that's kind of fun. It's really a symptom of the fact that I was involved in a field that was having its golden age, so to speak. So there was a lot of low-hanging fruit that could be picked by, the 17-year-old me and so on. But then I got my PhD when I was just turned 20, actually, at Caltech. I moved to the US by that time. at that moment, I was kind of like, I'd been doing particle physics, cosmology, and so on, going fairly well, but I kind of had outgrown the tools that people had built for sort of doing mathematical computation. And so then November of 1979, I kind of sat down and thought, okay, what's my plan? And the plan ended up being, let me try and build the best system I can that will let me do the science that I want to do. And so then, I mean, this is a shaggy story. I mean, then that turned into my first company. But in turning into my first company, it was kind of the mixture of companies and universities at the time was a fraught one. And so I was like, I'm going to do something. I'm kind of I'm going to do something that's fun. I'm not going to do the particle physics stuff that I sort of kind of said I would do, because I'm kind of fed up with the university story. I'm just going to do something fun. And I'd been long interested in the question of kind of how do complex things come to happen in nature? And sort of I tried, using the kind of techniques of all these, fancy equations and methods and so on from mathematical physics. Nothing really worked very well. I then started thinking about, what happens? What is the underlying thing that's in theories? Well, there are definite rules. How do you represent those rules?
But before we jump to that point, I do have a couple questions about the computers. So you mentioned that you had access to a computer in 1972 that had ferrite cores. So is this like a 16-bit machine? And more specifically, if you're trying to do physical simulations, computations with a 16-bit machine, you're going to have a very sort of hard time with the amount of memory as well as the precision relative to what sort of floating point representations you can make. So I'd be interested to hear about some of the specs and some of the challenges that you just had trying to use a computer to do effectively simulations in 1972.
It's an interesting story. Okay, so the machine I used was a thing called an Elliott 903, which was a British computer that is not well known. In a piece of very clever British engineering, somebody decided that it should have 18-bit words. So it wasn't a 16-bit computer; it was an 18-bit computer.
18-bit.
But it actually was like a 2 microsecond cycle time. So it wasn't super slow at that in that sense. And
500 kilohertz.
Yes. That's it sounds bad by today's standards, but so does 18 kilowords of memory.
Right.
The equivalent of about 40 kilobytes of memory. So there were a lot of. There were a lot of very practical challenges in using a computer like that. Like, you programmed it with paper tape. The number one practical problem in using it was it had an optical tape reader, and the paper tape would stream through the optical tape reader. Every so often, it would pick up a little confetti hole, and that meant that there was a bit that was wrong. And of course, that would then get loaded into the program in the memory of the computer, and it wouldn't work correctly. So, and the question, well, what do you do about that? Well, the manufacturer of the computer had this paper tape loader, which would read in the whole tape, and it would do a kind of horizontal parity check on each row of the tape. And at the end of reading in this whole tape, it would say error. So this was fairly frustrating, because then you would have to, the paper tape would go in a wooden bin, and you would kind of wind it back up again, and put it back and have to read it through again.
Wait, was this like a real type system, or was this like that kind of like stack of cards that would kind of lay flat?
This is paper tape.
Okay,
so it's a continuous stream of. It was 8-hole paper tape. Okay, so it had and it was. The kind of slow version of it, the way you would make the paper tape with a teleprinter, which had a little punch on one side, and then and then it actually had little sprocket things that would a little wheel that would go into the holes in the middle of the 8-hole paper tape, to move the tape along. But when you were using the computer, it was mostly using an optical reader, which would stream the tape through at a fairly high speed. But with this very practical problem of picking up confetti holes and so on, because that high speed meant you would generate static electricity, et cetera, et cetera, et cetera.
Was there the equivalence of whiteout on these tapes at all?
No.
Or would you just cut or you just had to start again?
You would copy. What you would do is there was a tape punch and tape reader on the computer, and so mostly you would just, to copy a tape, you would run it through the tape reader and at the same time be punching a new tape on the tape punch.
Right, but your programming, you would be doing it in RAM first, then you'd be saving it to the tape, or you'd be punching it on the tape to program.
Yeah, right. So what you would do is typically write out by hand a bunch of what you wanted to type in, and then you would sit at a teleprinter and you would type it, and no, you couldn't go back.
And if you made a mistake, you had to start again.
Pretty much, yeah.
Yeah.
It's I'm trying to remember whether there was any. I mean, the teleprinter didn't have any buffering, so yeah, that wasn't. For some reason, you would have thought that was a disastrous problem, but for some reason that was. I think you could. I don't remember doing this very much, but I think you could splice the tape.
Splice it. Okay.
Literally cut it and attach a new piece.
Okay. But, you could cut out your mistake.
Yes, right.
Okay.
But I mean, the thing that was one of my early achievements was writing a paper tape loader that would stop when it found the error. And then you could literally pull the tape back in the tape reader and it would resynchronize itself. And in modern terms, I had made up a kind of simple error correcting code, and I had these kind of block synchronization things that would, because when you pull the tape back in the tape reader, it didn't know where it was because you just literally pulled it. So it had to figure out, looking at the marks on the tape, it had to figure for the holes on the tape, it had to figure out where it was in the cycle of blocks on the tape and so on.
Right.
So that was probably my first piece of systems programming, so to speak, was creating a kind of error correcting paper tape loader.
So this is actually really interesting context too, because I have some background in modeling and simulation in another life for engineering systems, right? MATLAB, Simulink, we can do hardware in the loop, control systems, et cetera. But even in those systems, in that modeling, you always sort of are computationally constrained in terms of what you can do based off the hardware you have and how fast your control systems can run. And so it's actually interesting to sort of put in context the technology of the time, because and feel free to correct me if I'm wrong here, but if you look at cellular automata, right, you're trying to create a physical model that's in a highly reduced two-dimensional space, which is probably one of the only things that you could have really accomplished with that type of simulation technology for that time, right?
History is never as simple as one expects. So I should have done that, okay? But I didn't. I only ended up inventing sort of my version of cellular automata and so on after I had access to really quite powerful computers. So the narrative you just described is what should have happened. And in fact, bizarrely enough, it's what did happen, but I didn't know it, because I was trying to sort of one of my early objectives was there was a particular book that I got when I was 12 years old. That was a book about statistical mechanics, and it had on the cover this illustration of sort of a simulation of a bunch of balls bouncing around, sort of becoming more random and following the second law of thermodynamics. And so one of my kind of childhood efforts was reproduce that book cover. Now, many, many years later, I discovered that book cover was made on sort of the world's fanciest supercomputer at the beginning of the 1960s, and it was also kind of a fake. But I learned that many decades later. At the time, I was like, I want to reproduce this book cover, and I, understood about equations of motion and things like this. And you're absolutely right that on that computer, doing floating point arithmetic wasn't a thing. I mean, that computer had, what was it? It was the, which was it? It was the 12 instruction, I think. It had 16 instructions in its machine code. And I think it was 12 and 13 were the ones that did multiply and divide. Is that right? I think that's right. It was fixed point, integer-like arithmetic. And so I actually did try and take that simulation and turn it into something that was, in the end, actually a simple cellular automaton. But that wasn't how I thought about it at the time. At the time, I ran it, and it didn't work as far as I was concerned. Now, looking back years later, I realized that what I actually observed was a phenomenon that I observed years later in cellular automata, which was exactly the phenomenon that, in the end, was the core phenomenon that was the thing that happened on the book cover, which was simple program, simple initial condition, complicated behavior. If I had, it's sort of a typical thing in history of science. I mean, if I had had the intellectual context, I would have figured that out when I was 13 years old, but I didn't have that context.
Well, I think there's actually two pieces to it. So I think that one of the unique things that happened in your arc was not just the intellectual context, but also the curiosity. Because most people, when they look at these sort of randomized systems, sort of one of the first steps that you took was saying, well, technically this is deterministic, right? So I can run this forward, I can run this backward. So, and then saying, okay, I'm starting with this simple thing and my outcome is chaotic, right? Most people would maybe not try to dig into that. They just be like, that's interesting, but just leave it there, basically. Like, oh, there's some things that are coming out ordered, there are some things that are coming out chaotic. And sort of what you started to do is you started to try to understand just even what is chaotic, right? And you started trying to categorize what things gave rise to different types of behavior and why those behaviors would manifest. So you had to think about how to do the categorization, how to do measurements of properties of the system. And that's kind of where you sort of took what maybe somebody else just saw as like a curiosity, and you started to develop it into a science of sorts, which then, as you're absolutely pointing out, is trying to elucidate sort of the underpinnings of the second law.
The path, I've studied quite a bit of other people's history of science, so to speak, and it's always a bit shocking. It's always difficult. History of science is always difficult. How did you really get from here to there and so on? And I had one could assume that for oneself, one knows how one got from here to there and such like. The thing that has been quite shocking to me is that coming back decades later and thinking about what actually, why did I figure that out? How did I come to figure that out? I finally have figured out how I figured it out, but I certainly didn't know that at the time. All I knew was what actually, what I was doing. And so, a good example that I just figured out just months ago was, I had worked on computer algebra. And then I started working on simple programs like cellular automata and so on. And the question was, what was the connection between those two things? And I had kind of thought, well, there isn't really a connection. And I had realized just recently that actually there is a connection that's quite significant, which is that when I started using computers in the 1970s as a way of doing physics, I was doing algebraic computation. That meant that the answers I was getting were rich, complicated answers. And so looking at many such answers, I could get sort of intuition about what answers look like. If I'd been doing sort of purely numerical computation and just plotting, a couple of points on a graph, that wouldn't have been a sort of richness. The computer wouldn't have been generating sort of richness of output that could engage with one's intuition. And so for me, the idea that what a computer generates gives one intuition, I didn't realize until recently that wasn't, that had been a thing that had emerged sort of coincidentally from the fact that I was using computer to do things like algebraic computation. And so when it came to simulating cellular automata and so on, it was sort of obvious to me that the output you would get, you wouldn't just be trying to find, what's the number, what's the measurement I can make on this? It was the actual structure of the output that you should look at and try and get intuition from.
So this is interesting, and I wonder if this kind of maybe has some underpinnings to you stepping away from particle physics. If you look at particle physics at this time in history, and this is me just expressing my understanding of it, so feel free to correct me, but you're talking about experiments that needed a lot of money, a lot of years, and a lot of time to verify math that at that point I think was relatively well known. And so a lot of it was sort of these very long-term, very highly collaborative experiments. But one of the things that you're kind of getting at here with, your simulations is that you can run simulations quickly, iteratively, and sort of cheaply, relatively speaking, and actually get a result to then refine your intuition about the system. Whereas with particle physics, like, you could take decades to may or may not get a positive or dispositive result on your hypothesis. So is that part of what drove you sort of down this path?
Well, several points. I mean, first of all, the thing, in order to be able to do sort of doing creative science is made a lot easier if your kind of discovery loop is shorter. And, I've done computer experiments, not physical experiments. I have spent the last 45 years building a technology stack to make me very efficient at doing computer experiments. And that's critical because, I have an idea, I can, type away for a few minutes, and now I'm testing that idea. Now, you might have thought, well, if I believe in my idea, I could spend a month figuring out how to test the idea. But the fact is, one doesn't. And I can see, in a lot of things I've done, including things like our physics project and so on, it's as the capability to do these things gets to the point where you can do it on a whim, that's when you actually do it. Because you don't do the kind of, I wonder about blah, if that wondering is going to take you a month of work. You only do that when it's kind of below the threshold where, it's actually easy to do. And that's required, it's required 45 years of technology development, basically, to get to the point where it's really this ergonomic thing that you can kind of take an idea and try and sort of test it very quickly. But yes, in the days of particle physics has gotten bigger since those days. So it was, the typical experiment in particle physics about at that time was kind of, it was a couple of years. It wasn't like decade type time scale. I mean, building accelerators was decade type time scales, but I think the kind of the artificial physics that I ended up doing was its cycle time for getting a result was minutes rather than years. And
so there's a parallel sort of with the work that we've been doing at Quai, and that the blockchain systems, right? There's kind of like two sort of thoughts, right, in terms of like how this sort of world works relative to, information theory and distributed systems. And one of those sort of in the academic world is you sort of rigorously go through lemmas and proofs against some sort of, model to try to prove something about a system that is theoretical. And we took a very different approach in that instead of sort of obsessing over the theoretical, let's try to implement, test, observe, gain intuition, and then refine a hypothesis, and then just keep doing that, right? So it was kind of the engineer's approach to figuring out like what you should be doing to sort of get to the end result. And that I think served us pretty well here in the end. But I will say if you can't run simulations, it's very hard to move forward because you can't, either prove or disprove your hypothesis quickly. And the nice thing about computers, too, as you say, is you can get more data rather than just a graph. And if you look at the data you can understand it such that you can get an intuition about it to then help inform a better hypothesis. So I actually remember times when we were working on consensus, I would literally sit and I'd be staring at the code as it was making choices, trying to understand what type of choices it would make, why it would make those choices, to refine my intuition about what is good and bad, and circle back on the hypothesis. So very, very interesting path, right?
Right. With that type of thing, the real question is, computers do what they do. How can you get the best idea of what they're doing into your mind? And for me, sort of the whole visualization story ends up being the critical part. And what's non-trivial there is, computer experiments, designing a good computer experiment is difficult, like designing a good physical experiment. And a big part of that is, okay, there's something complicated going on inside the machine. What's the best way that we can get as direct as possible a visualization of what's happening so that we can engage with it in the best possible way with our mind, so to speak? And it's often taken, I've progressively gotten better at figuring out how to do that. And it's been a long process. I mean, a recent thing along those lines was figuring out kind of a way to visualize what's happening inside machine learning, which is something that, usually a neural net has lots of weights and connections and so on. There's no real way to get an intuition for what's happening inside. And I finally was able to sort of grind it down to the point where you can actually make pictures and see what's happening. And it's kind of complicated, but you can understand that it is complicated rather than whether what's fundamentally going on is complicated, rather than just that the thing is kind of smothered in complexity from the very fact that the neural net is set up that way. But yeah, I think I think you were making a point earlier about sort of the importance of randomness, so to speak. And, my own journey with that has been a long one, starting with this textbook on statistical physics that I was very enamored of when I was 12 years old. And looking back, and again, it's clearer to me with decades of, in between, the thing that was most exciting to me about that was the fifth book in a series of physics textbooks, each about different areas of physics. And all of the other books just said, this is how electrodynamics works. This is how relativity works. This is just the world, the universe just gave us these equations and now we get to solve them. The book about statistical physics claimed something different. It claimed from sort of the microscopic dynamics of particles bouncing around, we can derive the law of physics that is, for example, the second law of thermodynamics. And that, in retrospect, more than I really felt it at the time, was something that I found really interesting, that it was possible to derive the laws of physics, and rather than just be handed them, so to speak.
Right. So like, there's a couple just comments I want to make there. So when you're talking about experiments, I think we can agree that experiments are sort of very valuable, and that's ultimately kind of how you have to sort of do science efficiently. One thing that I've noticed, having gotten my PhD and done science, so to speak, is the people that are really good at it, sort of, there's an art to it. And the art form is they're able to ask the right questions, and then they're able to artfully design the experiment to answer the question. So you can look at experimental design, and somebody who's sort of new at it will make an experiment that's very costly, very complicated, and sort of takes a long time to run. But somebody who's sort of good at it, has experience, is they can figure out how to get it to the one isolated variable parameter question that they want, and they can run it sort of 10 or 100 times more efficiently because they sort of know how to do it. It's sort of the art of the science. But the other point that you just made was quite interesting. The reason that you were attracted to
let's talk about
the second law. Yeah.
Before we go off experiments, because I think there's some interesting things to say about that. I mean, one feature of how do you do science and how does experiment relate to theory and all those kinds of things. The thing that I think you're absolutely right, that knowing what question to ask in doing, for example, science research, as in entrepreneurism, so to speak, probably the most important thing is knowing what question to ask, not necessarily the mechanics of how you get the answer. But the thing that tends to happen is, you say, well, there's experiments you can do that are sort of the ground truth of what's happening. You have to have some hypothesis before you even imagine doing the experiment. But that hypothesis, in a sense, is telling you what you think the answer to the experiment will be. So one of the tricky psychological things in doing science is you have to be convinced enough about the experiment and what's going to happen that you have a hypothesis that you mount the experiment to test it. But you have to be not so committed that when the chips fall, how they fall, you don't kind of chase them and say, but it's got to be that way type thing. So it's a tricky thing to have, and it really matters how clean the experiment is, because if the experiment is very clean, there's no wiggle room. The chips fell this way, and that's how they fell. And if the experiment is kind of messy, it's like, well, the chips fell that way, but, there was this other thing that happened, and maybe it's kind of like we can kind of squidge it around. And this happens, more dramatically probably for physical experiments, but it happens in computer experiments as well. And I think that's that's a large piece of kind of what it takes to do successful experiments. I will mention one other thing about experiments, which is perhaps an interesting thing to reflect on, which is that I started off doing particle physics in a situation where there were physical experiments that could test the theoretical predictions I was making. And I had this experience, 1977. I was working out the consequences of QCD, theory of quarks and gluons, for production of charm particles, that was a thing in those days. And so I had a prediction, what should happen. And it was a very solid prediction that really depended only on kind of the structure of QCD and so on. But there was an experiment people had done that said the rate at which these particles would be produced or whatever was, 10 times less than the rate that I said they would be produced at. And so it's like, what do you do in that situation? Because, the kind of the traditional sort of, arc of science is you make a theory. If the experiment doesn't agree, you throw away the theory. I was pretty sure the theory was right. So
you got to redo the experiment.
What's that?
You got to redo the experiment.
Well, yeah. So what happened, my big mistake was I didn't actually go to visit this experiment. After this experience, I went to visit any experiment that I was kind of involved in talking about the results of. Because, any experiment where you see nothing is always a bit suspect. And so, it turns out the experiment was wrong. But the experiment was difficult, as leading edge experiments always are difficult. And so, I had this experience multiple more times where there's a theory, there's a certain cleanliness to the theory, there's a certain kind of conviction that one has, this theory is going to be right. And, then the experiments come in, and sometimes it's like, yep, the experiment verifies the theory. You're like, yeah, I don't know, this experiment is kind of messy. I don't know whether it really was done right. It's nice that it verifies the theory, but I'm not taking it that seriously. And then there are other ones where the experiment says, no, it's inconsistent, there's an anomaly of some kind, and turns out the experiment is wrong. And it's the vision that people sometimes have of science, where it's like, you come up with a theory, and then the experiment tells you yes or no. It doesn't really work that way. It's more complicated.
Yeah, well, I think too with the with science, if we kind of get into the art of the science, so to speak, when you're setting up the experiments, you want to design them as cleanly as possible, but then you also want to sort of have the intuition to be able to give scrutiny to the setup and the result to sort of put it in the proper categorization of meaningfulness relative to the theory. But then the other thing is, the more times that you make the hypotheses and are able to test them, the sort of better intuitive mapping you get about forming your hypotheses, so you can make more intuitive leaps about what to test. as a person, who works in engineering and science, I very much think that you always want to get to experimentalism because that's the only way to really make sort of like intuitive progress. I do want to circle back on that comment you made about the second law, because that's a very interesting comment. If we look at all the other laws, they are sort of reductionist descriptions of observed behaviors, if you will. Whereas the second law is the only one that effectively you get complex emergent behaviors from a very simple system. So one is sort of a reductionist thing, maybe, and the other one's an emergent thing. Feel free to give a better classification there, but
that's what I thought until about 2 years ago. What you just said is what I thought. So in other words, that we try to describe the world. It turns out there are certain underlying laws like general relativity, like quantum mechanics, and so on. And those, we have all these phenomena in the world, and we grind it down to the point where we can say, yes, it's just general relativity. Yes, it's just quantum mechanics. And that's how we describe the world. One of the sort of big excitements for me in the last couple of years is getting convinced that one can, like the second law, one can derive general relativity and quantum mechanics. They're not things that are just wheeled in as the way the universe happens to be. They have to be that way. And that's something, just as one imagined that the second law might have to be that way, just based on the properties of statistics, the properties of mechanics, and so on. And so that's kind of I would say the biggest, for me, one of the most exciting kind of philosophical consequences of our physics project is the idea and the details of how one can expect to derive the laws of physics. And we can talk. This is something of a hill to climb to get to the point of talking about how this really works. But
I mean that's kind of getting to the peak of the arc, if you will, right? Because I guess what the difference is historically, right? If you look at relativity, you kind of had a hypothesis about sort of the description, and then they did sort of this macro thing as an experiment, right? I think the first thing that validated it was a star during an eclipse going around Mercury, if I recall correctly.
Those are two different effects, but yeah, it's a little bit of a complicated story. It's another one of these experiment and theory kind of do a bit of a tangle.
Well, but what you're doing here is, instead of saying you're getting sort of an emergent definition, you're observing behaviors, and then you're trying to create sort of the minimalist description of the observed behaviors, and then test your description to see if they match, right? Whereas if you look at, sort of the emergent systems, you can ultimately derive those same equations, but you're doing it as an emergent property of complexity from a very simple starting point. And that's really sort of the difference, I guess, if you wanted to define it in some ways, of the Wolfram Physics Project, is instead of saying, what do we think the reduced representation is, we're saying we're going to start with the simplest representation and show that we can actually derive many of the reduced representations that we've already proven to be somewhat accurate, right? And then the expectation here, I assume, is that the sort of incompatibilities that happen on some of those reduced representations may go away because the emergent representation is very subtly different. So you kind of agree with traditional physics 99% of the time, so to speak, but the 1% is where sort of the resolution of conflicts lie, which is a very interesting approach, obviously.
I think one thing to say is that our ability to do Wolfram Physics Project today leverages the fact that we've already used the reductionism of 20th century physics. We don't have to say, let's look at all these different phenomena in that, in atomic physics and this and that and the other. We can already use the fact that all those phenomena we know have been successfully reduced to the description of quantum mechanics. So if we can get quantum mechanics, we know we can kind of fan out and get all of those other phenomena. But to your point about what yes, we will get, we get quantum mechanics, we get general relativity. Yes, there are subtle differences that we need to explore more. I mean, one of the things, so one of the big things that I'm interested in right now, actually, is figuring out the right experimental implications to actually go look for. And then, if we're lucky, there'll be experiments that can be done now rather than 200 years from now.
That's an interesting thing, because I've watched you on some podcasts with other sort of theoretical physicists, and right, that is kind of the question they try to sort of put the screws to you on, is what is one of the testable hypotheses that Wolfram physics can propose that isn't proposed with normal physics. Are you at the point that you can share one of those at least a high level, or are you getting pretty close?
Yeah. I mean, there are lots of them actually. I mean, so one problem is there's one parameter. It's pretty good if you have a model with just one parameter, but there is still one parameter. And it's basically what is if space is discrete, what is the discreteness length? Mm-hmm. That's related to the discreteness of time. It's related to the maximum entanglement speed in quantum mechanics. Once you have any of those things, you've settled this parameter. Now, in the past, sort of, this question of is the universe discrete or continuous has been one that's sort of been debated since antiquity. And people wondered about that for matter until the end of the 19th century. How do you do experiments that can tell whether Wolfram Physics Project is needed or whether kind of all the old stuff is just fine, even though the old stuff doesn't quite fit together quite right. But, either as it may, what's the smoking gun, so to speak, of something new? And we have in this whole theory, one of the more amazing things is that there's only one fundamental parameter, which is essentially the elementary length, the shortest possible distance, the elementary time, the maximum entanglement speed. These are all related. Once you have one of them, you have all of them. How big is that number? How small is the discreteness of space? We don't know. Are we going to be able to do experiments that probe it this century, this decade? We don't know yet. I will say that, historically, there was a question from antiquity on of are things in the universe discrete or continuous? So, for example, is matter discrete or continuous? And people had sort of wondered about molecules in the 1600s and even before that. But it was only at the end of the 19th century that people were sort of lucky enough that molecules, as they are making up matter, are big enough that you could observe their effects. Actually, a little bit embarrassingly, Brownian motion, which was one of the final giveaways, had been discovered in 1830 by a botanist. And the fact that ended up being the final smoking gun sort of thing that revealed the existence of molecules and so on was something that you didn't even need to do a new experiment. It had been done 70 years earlier, but you just had to understand the interpretation. Now, back in those days, beginning of the 20th century, most physicists believed that space was discrete too, but they couldn't figure out how to make the math of that work. And so by the 1930s, 1940s, it came to be sort of assumed, well, matter is discrete, light can be thought of as discrete, but space is continuous. And that became sort of the accepted doctrine in physics after that time. Well, we don't think that's how it actually works. How does one tell that? Well, so Einstein was kind of lucky when it came to general relativity, because it turns out that there are some parameter-independent predictions in general relativity. So he had a parameter too, which is the cosmological constant. And he didn't know the value of the cosmological constant. He had no idea what it was. The expansion of the universe had not been observed, et cetera, et cetera, et cetera. But there were predictions like that light would be bent twice as much when it went around the sun as the traditional theory had said, things like that, and which were independent of this parameter that existed in the theory. So, we have some parameter-independent predictions. One of the more bizarre ones is the existence of dimension fluctuations in the universe. We think the universe is three-dimensional, but actually in our models, their dimension is a dynamical variable. So there can be fluctuations. There can be a place that's 3.01 dimensional, 2.99 dimensional, etc. And so one of the things that I'm interested in is figuring out, can we observe dimension fluctuations? We don't know how big the dimension fluctuations left over from the early universe might be, but could we observe them if they're there? One thing that I suspect, we'll see how it plays out, we might know this year, I don't know, is there are many mysteries in physics. And the question is, are some of them things that are related to things we now know from our physics project? So one of the mysteries is dark matter. And the fact that, you look at a galaxy, it seems like there's a lot more stuff in the galaxy that's producing gravitational effects than you can see in luminous stars and so on. What's going on there? Well, that effect was observed 100 years ago, but we don't know what it really is. I think there's sort of a fun analogy, which is in the early 1800s, people were wondering, what is heat? And they said, well, heat flows from one substance to another. And so what heat must be, it must be a fluid of some kind. They called it caloric fluid. And they had a whole theory of how caloric fluid works. Turns out heat is not a fluid. Turns out heat is a feature of the microscopic motion of molecules. But that wasn't something you could even really imagine until you knew molecules existed. And that was my guess is that dark matter isn't matter at all. That dark matter is a feature of the structure of space. And it's what I've been, just as a kind of, it amuses me because of the arc of the history of science that it reflects. I've been calling it space-time heat, because I suspect that dark matter is a macroscopic manifestation of microscopic processes that are associated with the underlying structure of space and the discrete underlying structure of space. We'll see if that turns out to be right. But
yeah, it's actually interesting. When you read documents in your book, in a number of the chapters, you actually go to like original source documents on sort of as theories are evolving, right? You don't sort of read the textbook. You actually go back to the author's manuscripts that define sort of what it was, and you bring it forth in their own words. It's interesting, specifically with Einstein. If you haven't read it, you probably have, but I don't know if many people have read it. He actually did sort of like the sort of layman's version of general relativity in like a 60-page book. And it's interesting to hear it kind of in his own words. And one thing that is brought forth is that when he starts out, he says, I'm assuming the speed of light to be this sort of fundamental limit. I don't know why. I don't know where it comes from. We're not going to answer that question. We're just going to put it on a shelf and like we'll keep going, right? And then sort of like here's what happens once we do that. But that like assumption and why there would be sort of a speed limit to the universe is like a very interesting one. And that it doesn't feel like if you live in a continuous system, you should just have sort of like an artificial barrier limit. It kind of sort of in that assumption implies that there's some discretization of space and potentially time, and that's why you ultimately get that limit. It's not just some sort of arbitrary property that exists. It's an emergent property, right? But he sort of didn't want to talk about that. But if you like ask yourself, does that make any sense? It doesn't really make sense that it's just this thing in continuous space, right? And that's always frustrated me as someone who has taken physics. I could never get physicists to really discuss that topic with me. But I do think
it's an interesting point of view. I mean, my slight sort of pulling back from that will be the following. The speed of light is, in a sense, just a unit conversion between space and time. In other words, when a certain amount of time elapses, what is the corresponding amount of space? What is the corresponding kind of region of space that can be affected and so on? Now, if the speed of light could be infinite, one could imagine a situation where the speed of light was infinite. If it's, I think that sort of a question of what, well, okay, so I'm not sure. It's an interesting thought that that it's sort of obvious that it's obvious that the speed of light is, I'm not sure it's obvious either way, but in the finiteness of the speed of light in a discrete system, given that effects are somehow local, goes without saying, so to speak.
Mm-hmm.
The finiteness of the speed of light in a system where you're just describing it sort of mathematically in terms of continuous variables doesn't so much go without saying. In fact, for example, the diffusion equation, the heat equation, effectively has an infinite speed of heat built into it. In other words, at the first moment that you start putting heat in somewhere, there's a tiny amount of temperature change that happens even infinitely far away, and which is different from what happens in the wave equation, for example, for light, where you say, I start a piece of light here, there's a light cone, there's a limit to how fast the light goes. So yeah, it's interesting. I actually had not thought about it that way. That's an interesting, maybe that's a clue that should have existed from 125 years ago.
So and the interesting thing is, if you read the primary source, and you think about it, it's like it's not as hard to get to that conclusion. If you read kind of him putting it on the shelf as he's doing it, right? And that's actually the origin of sort of my uh, dislike of theoretical physics as it existed in my studies, was that insight. And I will say, in 2020, when you published your blog, I was like, this guy gets it. Uh,
Okay,
so,
I didn't think of it that way. So that's interesting. I have to say, in uh there are, once you're sort of bought into the discrete finite computation way of doing things, then the story of the speed of light essentially becomes a unit definition. But it's if things are sort of computationally finite, you're pretty much stuck with a finite speed of light.
yeah. Yeah. So one of the things that I think is kind of really interesting, that you've come to with um, cellular automata and this whole conversation, from my perspective, is obviously we're talking about discrete uh, space time, and you come up with this phenomena of causal invariance to describe things, and I personally like it much better than a lot of the commonly accepted sort of interpretations, because the things that sort of rub against one's intuition um, don't seem to be there anymore, but the phenomena to what things are measured still play out in a setting and this causally invariant. And so that's obviously one of the things that hugely appealed to me sort of following your project, is that one, you've discretized space-time, and then two, you make a causally invariant setting which describe phenomena observed through relativity, but doesn't sort of give rise to, again, sort of things that don't intuitively sort of make sense. Um, so I'd like to talk about causal invariance, and one thing that I'd like to talk about is the time invariant nature of the statement of causal invariance, right? So when I think about causal invariance, and maybe you want to just give a definition sort of first before I kind of opine, but yeah, yeah.
Well, I mean, so it's a little bit complicated. I mean, what happens in the world? Well, we think of it as a bunch of discrete events. There are discrete things. There's sort of a discrete data structure for the universe, but there's also discrete processes that go on. There are discrete events that update the data structure of the universe, so to speak. And the thing that ultimately is the only thing that is relevant for an observer like us is how do those discrete events, how are they connected? How are they causally connected to each other? So an event happens, it is, it's like a function where it takes in certain inputs, it computes, generates certain outputs. The question is, there will be another event, another function effectively, that takes certain inputs, produces certain outputs. There's this network of causal relations between those events. And that is the ultimate sort of representation of reality that we can kind of lock into. Now, as we try and kind of parse that causal graph of relations between events, we tend to think about space and time as being separate kinds of things. So we tend to think about the universe as there's a state of the universe at this moment in time across all of space. Then there's a subsequent state of the universe at a new time all over space. And that requires us to take this causal graph and say, okay, these events in the causal graph are happening simultaneously. These events are happening later, so to speak. And there are many different ways we can slice the causal graph, foliate the causal graph. Those are different possible, in relativity, we think of them as different reference frames with which we understand the relationship of space and time. And the sort of one of the key things of causal invariance is that there's different ways to think about this, but the one key consequence is this phenomenon that sort of the physics stays the same independent of how you foliate the causal graph. At a different level.
Well, and so that's the underlying point of that term, which is a causally invariant multi-way graph will end up having the same outcome given the input events, right? It just is
Yes.
It is an inevitable sequence that must take place under some time, but the result is deterministic, right? Just as cellular automata sort of are deterministic in their flow. So
yeah, you're bringing in another point here, which is, I mean, it's a slightly complicated concept, but the other point is you can have these events. These events can happen in different sequences. You can represent, you can have a multi-way graph that represents the different possible paths of history, and sort of the key idea in the end is that full causal invariance story is a little bit more complicated because it also deals with infinite processes. But the finite version of it says, well, you can take two different branches of history, but in the end, they will always converge, and you'll always get the same outcome, so to speak. So kind of an everyday version of that is, you learn to do algebra, and you learn that you can multiply things out, or you can sort of add things together. You can do it in any order you want, and you'll always get the same answer. So at the intermediate stages, you'll get different results, but the result of following the path all the way will always end up at the same result as following a different path. So that's kind of the.
So yeah. The thing that I'm driving at, and this actually came up in our last conversation a little bit when we were talking about blockchains, and I've had time to sort of reflect on it. And it's one of the reasons I want to bring it up because I think it's sort of a subtle difference here is in thinking when you look at causal invariance, we're basically saying that the execution of the states will always get to the same results, sort of given the input, right? And we're talking about you've talked about like space time and you've talked about or time like hypersurfaces and space like hypersurfaces. Sort of in my thinking of the world, I don't think about time at all. I only think about it as sort of a space like hypersurface. And then what we're doing as humans is we sort of experience from our point of view the evolution of the states, and we impute upon that evolution this proximal concept of time. But time is just us sort of experiencing the evolution of state from our perspective. And that's why when you sort of think in space-time, you'll have different observers that are having different perspectives of the evolution of time. But time is really just them seeing the evolution of those events transpire differently in different orders based off where they are in space. So I guess they're very sort of specific.
This is a tricky business, okay? Because let me hear, you know, one view of the universe is all of space-time already exists. We're just traveling through it. That's one sort of point of view about what's going on. Another point of view about what's going on is there are rules that determine how the universe works. And at every moment, those rules are being applied and they're building the future, so to speak. So, but these two points of view are actually, in some sense, very similar. Because if there's a definite rule that builds the future, you just say, let's look from outside the universe. Let's look for the whole thing that got built. It'll be a determined thing that got built. That's this whole multi-way structure of all the possibilities of possible paths of space-time and so on. And so then the thing you have to realize is that observers like us, being sort of computationally bounded, we only get to sort of ride on what the universe is doing. We don't get to say, oh, I can sort of simulate what the universe is going to do and know what's going to happen. It's just like there's all this computation that has to happen to see what will happen. In the view where the future is being built incrementally, it's like all this computation is happening right then and there that's building the future. And we are, we're sort of piggybacking on this to find out what happens in the future. In the other case, the thing is already built in some sense. It's already determined. It's already there. It's the result of whatever was done on the other, in the other point of view. But we, as observers, are only capable of exploring that at a very small rate. So, in other words, in one case, it's built, as we're watching it. In the other case, it quotes already exists in some sense, but we are merely getting to explore it at a small rate. I'm not sure if that's helpful to what you were saying.
No. I think that is. So I guess I've fallen to this latter view of sort of everything is determined. We're just along for the ride, and we're kind of experiencing it, in our sort of limited computational space. But I think it's interesting. I think my intuition diverges slightly because I'm doing sort of the blockchain system with Quai. And so if we can get to sort of a little bit of concrete reductionism there, I think that the point might be well made. So just to give a little bit of context, Quai is a scalable hierarchy of proof-of-mind blockchains that uses a novel consensus mechanism called POEM, or proof of entropy minima. The interesting phenomena about this system is that it is a causally invariant multi-way graph. Then we discussed this in length last time. So one of the primary things that you're trying to do in the blockchain system is to be able to choose which block to call canonical at that point in time and to mine on. And one of the things that happens is that because you have, which is very interesting, an analog here, a computationally irreducible process mining taking place in a geographically distributed space, you end up with space-separated events, which then take time to propagate such that everybody participating in the system can see the same information. And so very practically speaking, a blockchain, what that manifests as is if somebody is producing a block and it takes time for it to propagate to the rest of the participants before they stop mining their current block and start mining on the new block. And so in that time that it takes to propagate, you can have another participant also mine a block. And then you suddenly have two blocks that are propagating in the system, and you have to choose which one you want to adopt. And so with POEM, we have a deterministic rule that allows us to choose which block to adopt. And it also has the property of being Nash equilibrium. And, eventually we can say that it's causally invariant. But when I think of this problem of sort of the origination of block A and block B, one of these will deterministically have a better entropy weight or entropy minimization than the other. So when we were previously talking about it, you were kind of thinking about it as you were saying there's sort of an origination event, and then sort of when they collide, there's a resolution event. But when I'm thinking about the system, I'm thinking about it strictly in a space-separated manner, meaning once block A is produced, right, then say B gets produced, it doesn't actually matter which one was first or second, but the existence of those two blocks, the resolution event is determined by the second event, right? So the second event is simultaneously the resolution event. There's no sort of third event when they collide and the information is known, because it's a deterministic outcome once the second event happens. So another way to sort of put this simply is, if B is the heavier block, once B is produced, everybody knows that like B will be chosen because it is the heavier block, even though not everybody has yet seen that block. So I know that when you see block B, like you will choose it over A, even though you have not yet seen B, but the resolution is determined by the production of B. It doesn't actually have to propagate to create a second sort of event that's resolved. So another way to put this in the blockchain system is by running the code with the same genesis block, we are always in consensus from that point forward, because any event that takes place has a deterministic outcome, right? So when I'm thinking about this and then I'm applying it to physics, I am thinking about this as strictly a non-temporal process, because no matter when I see block A and B, no matter when it was created, if I come back a year later, I come back now, I will still say that B is greater than A. Right, every time. So that is what makes it causally invariant. In saying that, I am also actually saying that it's time invariant, meaning the outcome has no bearing on time or the relative time to when these things were produced or when I see them. It is just a consequence of the causality of the originating event. If that makes any sense.
I have one comment to that, which is, you say A was produced, it's out propagating in the system, whatever. Then B is produced, and as soon as B is produced, you know it's a winner relative to A. But in order to know it's a winner, you have to do the comparison. So the question is, it's a question of what level of sort of modeling you're doing. There has to be somebody doing that comparison. There is a comparison.
But when I do the comparison, I know that the outcome will still always be B. So the statement of causal invariance is to say that the outcome is determined by event B taking place. I don't actually have to do the comparison between A and B, because it will happen in a causally invariant way whenever A arrives to the spatial location of B.
Right, but it has to actually happen. In other words, if A and B, let's say that A and B were being mined in geographically different zones and they just never, they never interact. Then this will never, the comparison, knowing that B was the winner, will just never happen. There has to be some comparison moment where somebody notices that A and B are both in the system and oops, B is the winner, let's throw out A. I think that, imagine that they're really separate. There's an event horizon between them. Then I just don't think that they, I think they both float as separate, consensus winners, so to speak, until that moment when there is a comparison event, which something you can think of as a comparison event that resolves them. I think.
But like if we like internalize that concept of causal invariance in the graph,
yes,
the origination event determines the outcome. So now what you're saying, and I'm thinking about this sort of from the practical blockchain model, right? What we would say is that as long as the system becomes consistent, we will be guaranteed to have consensus, right? So the outcome of the comparison is known as long as we just see all of the data.
Right. That's right. But you have to, you say becomes consistent. The question is, what are you modeling? And if you're modeling every sort of, that you could take the point of view that is in quantum mechanics, for example, you model, in typical quantum mechanics, you model all these underlying quantum processes, and then there's just this measurement thing that happens. And that's a separate kind of thing that you don't model in standard quantum mechanics. I think similarly here, you're saying you could imagine a measurement phenomenon happening that is this comparison that is not part of the modeling of what's going on in sort of the underlying block origination and so on. I don't think, I think in the end, it's the question of whether that matters. For example, imagine the case of these blocks being mined in two separate zones, which don't communicate with each other. I really think then you don't reach, your poem mechanism doesn't kick in, because there was no, the folks on one side just didn't know there was a lower hash somewhere else. They have to have that interaction. They have to, you talk about it becoming consistent. There has to be interaction for that consistency to be established. And that interaction, you could break down the interaction into a series of elementary events. You don't have to do that. You could say, I'm just going to have this global measurement process happening. But I think if you do break it down into elementary events, I think you're going to end up with a comparison event, which is going to be the one where you pick B over A. And I mean,
so like, let me try this in a slightly different way. So when I'm thinking about a causally invariant graph, right? What we're saying is that given a certain set of inputs, we will get the outcome. So with the concept of A and B here, and back to just this concept of like the universe has already happened, we're just sort of riding on it. I guess my statement is I don't think that there's really a delineation of saying that there's an outside observance to the system. It is just the progression of the events in the graph. And there's no such thing that's meaningful to say that you have an observation. It's just the events take place and they will intersect or they won't intersect. It's just when they do intersect, the outcome of that intersection and that convergence, what's going to happen, so to speak, even if you just look at A and B. And that's what we mean when we say causally invariant. And so by implication, then I think you're also saying that it's time invariant. Or to put it another way, I don't think time exists. Everything is just like space-like events that may or might not intersect with each other. That's at least sort of the intuition I get from having built the macro sort of analog to the system. And I just think it's interesting to discuss with you because I know this concept of like an observer and observation events in physics is like a very controversial sort of subject. But having done this sort of that macro work, that's how I think about it. So
here's where I think things get tricky. I think that event horizons are a place where you might say time doesn't exist, but an event horizon is a place where, in effect, time is going infinitely slowly. You can't, something which might one day happen has been frozen out from happening by the presence of an event horizon. There is a causal connection. There could one day be a causal connection between this and that, but there isn't right now because there's an event horizon there. Let me make another meta comment before returning to that. Okay, my meta comment is one of the reasons I'm interested in blockchain is precisely because it helps humanize some of these kinds of questions and concepts that one can think about very abstractly in physics and so on. And I think it's really interesting to try and sort of live causal invariance effectively. I mean, it's really in my efforts to try and think about sort of foundations of economics and the relationship to what we think about in physics and so on. It really helps me to get a better intuition for how to think about physics, to think about these incredibly practical things. I think that the interplay between these things is really powerful. And that's, but now returning to causal invariance and its role in sort of everyday life versus, database consistency and so on, which are all kind of reflections of kind of the causal invariance story. I think, this question about, well, let's talk about observers. Let's talk about whether observers matter. I've been sort of studying different kinds of systems and different kinds of observers, physical observers who really care about time, mathematical observers who are exploring the giant network of all possible theorems, and it's not clear that time matters so much to them. It's more like I put this bag of theorems in my kind of collection of ones that I think are true, That's what matters. It's not so much the progression of how I do that. And there are different kinds of observers. And I think it is a non-trivial question whether the economic observer is I tend to feel, maybe I'm wrong, and don't think I've thought it through properly, that there is a time component, and it is worth thinking about. Okay, so here's why I would talk about an economic observer. My point is, you don't get a God's eye view of the economy. You have a local view, just as you have a local view of space-time. And in mathematics, it's a little bit more of a God's eye view, because it's like, I've got these theorems, they come from different places in mathematical space, I'm putting them all together. I mean, my guess would be that the way this will show up in your kind of setup is through things like these geographic zones that I think you have, of where consistency develops in that zone, and then there's consistency. I think you're calling them zones. Am I right?
Yeah, zones. That's right.
And somehow that's sort of as it should be, that you have an observer who is a zone 3 observer and knows nothing about zone 7.
Oh, except when zone 7 interferes with zone 3.
Well,
so
yes.
there's also, right, those events that do transit that do end up interfering, but it's only the events that interfere that transit, so to speak.
Yes, but you could imagine a zone 3 observer, gets on their instant messaging app with a zone 7 observer and says, oh, by the way, what's the hash of your block? That's something that's not part of that's something that could happen independent of the protocol and so on.
Well, but it would only matter if it was a block which had sort of protocol coincidence. So in the system specifically, right, it's merge mine. So when we find a zone block, you basically do a work algorithm, you get a threshold. If it meets the zone threshold, you have a zone block. Now, the way that we sort of weave the zones back together is we have the higher block order coincident blocks. So as you're mining, instead of just getting a zone block, maybe you get 5 extra sort of zeros, so to speak. So you meet the difficulty of region block. Now, that region block is important to any zones that are under that region. And if you get a prime block, that's important to all zones under all regions under prime, right? So when you're talking about 7 and 3 talking, it only matters that they talk about something that actually interferes in both sets, which are necessarily these coincident blocks, which give a mechanism by which they sort of asynchronously so they're propagating asynchronously, so they're like completely independent systems. And then statistically we sort of get these coincident events that force them to have sort of knowledge or shared state, which are these dominant blocks, regions, or primes, right? So when they get a region, zone 7 hasn't sort of seen it yet, but if zone 3 gets that region, zone 7 needs to know as a miner that I need to build a block on that next. And after that block has happened, I've now referenced state that left zone 3, or an event that left zone 3, which then will affect my state in 7. Right. So it's only through those sort of macro events that sort of transit the geographies, that it matters. So in the case of, somebody texting, and they tell me their block hash, it only matters if it's a region block hash. And then if it's a region block hash, sure, I need to know about it, and I can deterministically resolve what I'm going to pick based off the poem rule again, deterministically. So if they talk to me about it and it matters, meaning that it's reached that sort of geographically shared layer, we'll still be able to deterministically resolve it.
Right. No, I mean, I love living causal invariance, so to speak. And I think it's one of these things where when one thinks about things theoretically, and then there's a sort of practical manifestation, you get a somewhat different intuition from the practical manifestation. I mean, I'm not sure necessarily that we're disagreeing about anything about how, well,
No,
about how to think about
there's like, so from my perspective, right, I have an intuition, and I'm just trying to point out where I think my intuition diverges, because the intuition, I think, here is, again, we've gone through the system. They're very, very analogous. So the divergence of my intuition is in two parts, I think. One part is I just fundamentally don't think time exists. So when we talk about like time, like hypersurfaces, it's just sort of like a nice reduction of human understanding of like how we see the world, but it's not real. It's just our experience. We arrive at time. And it's interesting too when we're trying to prove something about these systems, and we're just like trying to prove that sort of like poem works and poem is secure, and is it safe, is it lively? In a time-based construct, it almost becomes incompatible. So if you look at sort of traditional information science, and they want to talk about proving things in these sort of time-based rounds, right? And poem is effectively incompatible with those models, but it's incompatible because time is a derivative of causality that doesn't exist, right? So like it's hard to then make a proof about something that's more fundamental than the derivative if you're using the derivative as the construct that you're trying to do the proof, if that makes sense. So like this sort of entanglement in information theory where we try to sort of prove these things using those time-based rounds, like, makes you very aware that time, is the fly in the ointment, so to speak. So that's sort of like one intuitive point. But then the other point that I would make too is that I personally don't think observers exist, because observers are always part of the system. So as I think about this, like, I can't say that there's like a God's eye view. I can't say that there's like an observer that's sort of outside the system making a measurement. The observer is part of the system, right? And there is no such thing as a God's eye view. You just have events that are propagating through space in a causally invariant way. So those are the sort of points of intuition where I think there's mild divergence.
Okay, let's take those apart for a second. It's
Yeah,
interesting.
yeah.
I mean, so you're, in a sense, poem provides a way of painting the network of events in space-time. It provides a unique way of kind of painting that you imagine all of space-time is built up, and now you're going to just, you can weight every event. Everything in space-time is weighted by your, hash number or whatever else. It's and so I think from that point of view, it feels very much like everything is already determined, because you could just at any, there is just a definite painting of all of those events just based on this one parameter. And so it feels to you a bit wrong that you say, well, I'm just exploring these events step by step, because you say, but look, I can just tell you the answer. Now, I think my response to that is, and this is where these sort of two complementary views of things. One, the future is built as we go. The future gets built as it, progressively the future is built. And there's this irreducible computational process that we can't speed up, that is just building that future. Then the other version of it is, future's already built. It was difficult to build that future. It was difficult to build the whole thing, but we ignore that. It's been built. And your, poem protocol, for example, is an example of something where it's easy to fill in the answer once all the details of what the possibilities are determined. I mean, knowing what hashes are possible and so on, that's difficult. But once the hash has been generated, it's easy to assess which one is the better one, so to speak. But then, then the issue is, okay, so let's talk about observers and whether observers matter. Okay. The thing is that if the entities in your system are, okay, so we have an inner experience of things that are happening in the world. There is sort of what's happening, and there's the inner experience encoded in a bunch of neuron firings or whatever else. And I think there is a meaningful way of asking, what is the translation from what actually happens in the world to that collection of neuron firings that is our inner experience of what happens in the world. There's plenty that happens in the world that we never reflect in our neuron firings. There's plenty of detail in the world that just won't fit in a finite mind, and we ignore it. So I think that there is a non-trivial step in going from the universe as it is, the universe as we perceive it, as we kind of make all those equivalences and say we don't care about this feature and that feature. We don't care about the precise positions of all the molecules in the gas. We only care about the overall pressure, let's say, or the overall velocity field or whatever. And that's so there is this step that is relevant for our perception of the universe, which is in the end all we have. And so the question is there, as we kind of think about sort of the network of space-time and so on, is what's important about that what we perceive of it, or is what's important about it what there is? Now, I think in your setup, there's an interesting question to me. I'm thinking this through. What is the observer in your setup? Or is it just that the blocks are what the blocks are, and they're an objective reality? Anybody can pick them up. And what's this about observers? Why do we care about observers? Right?
Yeah.
Okay, so here's my argument about that. Okay.
Hold on. I just want to interject on the example you gave between does the universe exist or it's already built, or is it something that we're progressing? In a deterministic system, that doesn't matter.
Well,
like that's like a question for the gods in some ways, right? Because like from our limited computational standpoint, it doesn't matter if it is existing or if it's contemporaneous sort of execution of a deterministic set of rules. And either way, you're getting a causally invariant outcome, right? So like,
sure.
right?
Yeah, right.
So,
It doesn't matter. It's simply a point of view. That's correct.
well,
Simply
but if that's the case, then I think there's some sort of analog that we build on top of that that does say that observers are part of the system and they don't matter.
well, except observers do matter, because the laws of physics will be completely different to a different kind of observer.
Well,
In other words,
that's just a different person. So that's just a person that's at a different point in space, right? But even when you say space time, I think that when you fundamentally get down to it, it's not space time. It's just space sort of events, right? So like the events happen and they happen in this thing that creates this causal order, but they only are happening in space. They're not actually quote unquote happening in time, right? Like if we just like throw time out of like our construct of thinking, it's just events that like propagate through these discrete computational machines. So like when I'm thinking about this, I'm thinking about this as the macro hypergraph all the way down to like the micro hypergraph. And for me, it's effectively a perfect analogy. So I've had to deal with like building the system and seeing how it behaves, right? And like trying to understand like what happens in those like macro events and how they propagate, right? When you find these blocks and like what happens. And for me, like the perspective is there is no time because the events just exist. And until I say that, like I have an observer or I have a godlike view, I can never tell you if A or B happened first or second. They just happened. And all I can do is causally order them based off the rules.
okay, so let me here's a way to think about this, perhaps. The as you go trying to do hashes and find the lowest hash and so on, your that is a process that gets done. And it is the question of an observer, I might think, in your kind of system is this, there is an observer who can find every hash that works. They can find the ultimate poem hash, so to speak, the lowest, the fundamentally lowest. But most observers don't find that. They don't know what that is. They find the one that happens to be found during the time that's available to go find hashes. So, in other words, just like an observer like us has certain limitations. An observer like us doesn't look at individual molecules. An observer like us believes, that there's a single thread of time, these kinds of things. So an observer in your system has the limitation that they only get to do a certain number of terahashes per second. And that means that there are parts of the multi-way graph that they will never visit. And so that's a reason why it matters that there is a reason why it might be useful to think about there being an observer, because the full multi-way graph that has every possible hash that works, just, if all you've got is, 50 terahashes to find that hash, you may not find it. And so it matters that it's you rather than another observer that's going looking for it. It matters what the observer is like, even though there is ultimately a completely deterministic multi-way graph that contains every hash and every winning hash, so to speak. And even though your protocol would absolutely tell you that in that multi-way graph, in that ultimate multi-way graph, there is a best place in that multi-way graph. It's the whole thing is kind of weighted in certain ways, but the observer, the poor little observer who's only doing 2 terahashes per second, is doesn't manage to explore all of it, and that would be in your context. I think that's why the concept of an observer might matter. And by the way, an observer, you could have different kinds of observers. You could have observers whose choice of random things to test the hashes of is different. And so you would have one observer who has this strategy, another observer has that strategy. These are like observers with different sensory systems in some sense, exploring this multi-way graph of all possible hashes.
So I don't see the miners as observers. I actually see them as being X the system. So if I were to make an analogy to your theory of physics, there's some computational limit which you apply to allowing the progression of the graph, right? Such that sort of gives rise to time, right? So there's some speed limit of computational capability, and that's also why we kind of observe in space-time that we can sort of move through time or we can move through space, and the idea being that you're sort of splitting the computation when you do one or the other, so then you sort of get retarded in the second, right? So
Yep.
I'm moving through space, I can't move through time as quickly. If I move through time quickly, I can't move through space as quickly, but vice versa. So from my analogy of the system, then I see the miners as that computational construct that's evolving the system, but it is like whatever that concept is of the property of space-time being able to make this like step, that is the miners. And it's only once the miners make a step, an evolution, a node, a block in this case, does the events process in the graph. So then sort of everything that sort of enters the system are the blocks themselves. The sort of things that are happening prior to a block don't exist from the point of view of this system. It is sort of that intrinsic sort of computational base, if you will, as the analogy of like what is space-time and what can it computationally produce. So like they are the construct that all of this concept is like built on, but they aren't actually a participant or an observer. They're the ones that cause the transition events to take place. Now, that's the mining, and then if like you're a node runner or you're a participant, you could very well be an observer, but the process of mining is sort of the lower construct of the system.
Well, I think that's in that the view you've just expressed is kind of the universe is built step by step, rather than the universe exists and we are merely passengers going through it, so to speak. So, I mean, you're saying the miners are sort of creating the future in the sense that they are the ones who are creating the causal graph that represents the history of the universe, so to speak. And the point I was making is that it's a little tricky because the miners are a finite resource. In physics, the universe, in some sense, the whole causal graph is being produced. The miner of the universe is, in a sense, infinitely powerful. whereas the minor, well, not actually infinitely powerful. The minor of the universe is able to follow every path. The miners who are doing some number of terahashes per second are following only certain paths, and they're leaving some parts of what could be mined undone. So they're leaving, the structure of the causal graph. Some parts of it they're filling in, some parts of it, oh, we didn't visit that part. And now, one interesting feature here is that your Quai protocol is basically saying it's talking about the whole graph. It's talking about it's making a statement about the whole graph, even though the miners might not reach the whole graph, even though the miners, it's telling you how to relatively weight the miners, but there's a super miner somewhere, a fictional super miner who is the ultimate, imagine a miner, sort of an interesting thing to say, imagine that there is a computationally infinitely powerful miner who can do the non-deterministic computation, who can sort of solve, who can set P equals NP, so to speak, who can basically decide that they're just going to explore every possible hash. And they're going to say, I got it. It's the absolute minimum. It's, no miner, even though it's, I'll win relative to any other miner. And I think that's, I think what the way I would see it is, it's sort of interesting because you're building your universe with finite computation. You're building the parts of the universe that you explore with finite computation. Whereas in the physics case, the universe builds itself with sort of the maximum possible computation, and we merely get to observe it. We are the finite ones making only a limited observation of the sort of infinitely powerful, not infinitely, but maximally powerful universe. It's very interesting. These analogies are very interesting.
Yeah, right. Well, and that's why I think it's productive to kind of discuss them. So it's interesting, right? You're saying sort of the maximally powerful universe. So sort of in the construct of a miner, if you had a miner who sort of had sort of very large computational ability, they would be able to transit both forward and backward through time. If as we construct time, right? Like that's like the implication of that statement.
Well, that's an even further thing, because I mean, I was simply.
Well, I'm just saying for my statement. I think if you extend it to your work, if you said that you weren't sort of a computationally limited observer, you'd be able to do the same thing.
Well, I mean, so both in the universe and in a blockchain, there's kind of something like a blockchain built up. I mean, there's a net of events that happen, and those events are sort of entangled with previous events. So in other words, the event that happens now, you can't just sort of zero out that event because it's going to be knitted into this whole structure of future events. I mean,
well, so in a blockchain, though, in a proof of work blockchain specifically, if you had infinite computational ability, you could zero out events because you can make chains that start further back, quote unquote, in time, right? And then you could sort of branch that chain off and like make a new history, right? So in a blockchain, if you had this infinite computation, you would never get finalization of any of the system because anybody could always go forward or backward sort of at will. In the system and rewrite every path. I do want to ask a question though. When we talk about the universe, you're saying it's maximally there, and you're also saying that you think it explores every path. It would be my intuition that, right, for us to sort of perceive time, that there is some computational resource that is available, and again, that's why space-time sort of has that trade-off. And so there's probably a finite quantity there, and you were saying that it's maximal.
Well,
So
I'm just saying.
No,
It's not an interesting statement. What I was saying there isn't interesting, and here's why. I mean, because all I'm saying is that there is no outer clock. So the universe just does what it does. And so in some sense, it could be looked at from the outside, which you couldn't really meaningfully do. But looked at from the outside, you could say, the universe is taking an immensely long time to to follow that branch. Let me give you an example. There's a one of the folks at Wolfram Institute made a little in-browser application that lets you explore multi-way graphs for the universe. And the question is, you're there, there's a branch of history, and you can choose to follow an event. You can choose to apply an event, or you can choose not to apply an event. In a sense, depending on what events you apply, that is, how to say it. I mean, the events are always applicable, but you may not have chosen to apply them. You may have, they are always, the kind of, there is no progression of time until the event has occurred. You can't say that. Put it another way. I mean, the statement that time progresses sort of in a maximal way in the actual universe is really a rather boring statement about units, I claim. In other words, there is a progression of things that will happen, that the rules determine will happen. Quotes, how fast do they happen? Well, they happen when they happen. The thing could be being built up, one piece is being built at this speed, one piece is being built at that speed, but until they're built, there's nothing to talk about. And there's no sense in which, you're externally determining the rate at which they're built. So it is reasonable as a matter of defining time units to say that those things are built at some sort of maximal rate, and that's what determines the ticking of the universe's clock. But I don't think that it makes sense to, you can't sort of say, oh, the universe has kind of gone lazy and it's not adding, this piece to itself, because nothing exists until that piece has been added.
So I've a couple sort of statements to follow down this path. So if we're saying that and I think we agree on the predicate that the universe sort of has a finite computational limit in both of our minds. So I would potentially argue that if you have a finite computational limit, I could then make the supposition that not all paths are actually executed, because then there wouldn't be a finite number of paths. That would be statement one. Statement two would be that
I think you're getting yourself in trouble there, because the fact is that with your statement that you consider that time doesn't exist and everything has already happened in some sense.
Well, but that question, the concept of a causally invariant system doesn't actually matter, right? It's like if you go to universe 30, in your cellular automata, right? Like you can know that the outcome is deterministic. So if the outcome has played and you're looking at a reference of the record, or if you're playing the outcome in real time from somebody in that system, it doesn't actually matter. If that makes any sense. They're still going to follow the deterministic path, regardless if it exists for them or not. The outcome is the same if it's happening in real time or if it's happening sort of as a record, right? But I guess my point is, if we assume the computation be finite, then I would also say that you can only follow a finite number of paths of execution in the graph. And I would also say that any observer that is part of this system means that they have a computation threshold which is lower than the system that they're in by definition, right? So, and this is the concept of a computationally limited, bounded observer. The ultimate bound is that you can't be more computationally fast than the thing in which you find yourself as the construct, right? So if all of those things are true, I think what you have to say then is, if there's a finite amount, not all paths are actually followed. They're possible, but they can't be followed because you have an infinite number of paths under the concept of finite computation. And then two, for a computationally bounded observer, they can't go forward and backward in time, which is one of the things that you obviously discuss. And then
wait a second.
There's one more thing that I have to say here is that when we talk about the progression of time, if we were to think about ourselves as part of the construct which is evolving, we actually would never notice the difference in time. The only thing that we can tell is the relative difference between two experiences of time across space. But like we wouldn't be able to, if sort of the simulation was glitching, let's say just we're in a simulation and the clock is
Oh, right.
is getting thermally throttled, we wouldn't actually observe that. We would only observe
Yes.
it if our clock was getting throttled and
Yep.
yours wasn't, and then we would suddenly sort of see a difference. But we, from an experiential point of view, would never know, right? Because
Yep.
like our reality is the clock step, so to speak. And I hate
Exactly.
using clock here because I'm trying to argue time doesn't exist, but you get my point.
Yeah, no, and I think you're absolutely right there. I think going back to this question about the finite observer cannot follow all paths, I think that's a little bit complicated because I think you do have to make a conceptual distinction between the view of the universe that says it's being built, built to order, so to speak, just-in-time universe building, versus the thing sort of already exists and we are merely traveling through it. In
So,
other words,
but okay, interesting. Okay, so the okay, so I guess when I said finite, I didn't mean from the observer standpoint. I meant from the universe's standpoint. Meaning, if we assume that this concept of space and time, right, is saying that we have a finite computational limit, that actually then is almost indicative that we're not sort of traveling through a predetermined thing. It's doing it in real time, because if that weren't the case, then we wouldn't see that relationship between the trade-offs of moving through space and moving through time.
I don't think that's right because I think that it is you still see that. Look, in quantum mechanics, there are these two different pictures: Schrodinger picture, Heisenberg picture. What changes? Is it the observer that's changing, or is it the system that's changing? It's the same type of thing over and over again, same kind of story. Is it the system is already there and we are merely getting to sample pieces of it, or is it that things are being built just in time, so to speak? And I think that the existence of a finite kind of limit on computational resources for the universe, that limit is a limit on the multi-way computation. It is not a limit on that there can be, just as there's a certain rate at which time is progressing, there's also a certain rate at which things can be branching. And that rate is finite, but it's not the case that one says, I'm sorry, you're out of luck. We can't go there in those branches. We've used our computation budget. It's kind of like whatever branch is, what can I say? This is tricky. I mean, the point is that you're building this causal graph or multi-way causal graph, and there is an ultimate causal graph, multi-way causal graph, whatever, to build that is abstractly defined. Now the question is, how did it actually get built? In what, did that branch get built? And that question, who cares what the answer to that question is until there's something perceiving that answer? In other words, from the outside, there's no meaningful way to discuss that. You could theoretically discuss it, but it only matters when there's a perceiving observer, when there's something perceiving it that's saying, oh, I saw that branch hasn't been built yet. I can't, I'm not, it matters that branch isn't there. If the tree is falling in the forest, to not mix metaphors with branches, and there's nobody there, if the branch happens in the universe and there's nobody there, it doesn't matter whether that you say that branch was formed or wasn't formed. It only engages when there's something that can perceive it. And I think that's where you knit together the view of things that is sort of the just-in-time universe versus the we're exploring it as we go universe. Now, I mean, let's try and bring this back to sort of the blockchain case, because I'm interested to see sort of how this anchors in something. I mean, from my point of view, the it wasn't built is the statement no miner mined the full multi-way graph. In other words, what matters to the miner, what matters to the blockchain, to the use of the blockchain, is what actually got explored on the blockchain, not what is theoretically possible at the level of the full multi-way graph of all possible blocks. It's and so that means that I think it's it's the same story. You could discuss the full multi-way graph of all possible blocks, and that will be one view of the blockchain: is there is a full multi-way graph of all possible blocks, but as the miners mine, they only explore some part of it, and as transactions.
So there's like another interesting analogy here, which is we do have branching technically, but like the goal is to keep the branching finite,
Yep.
sort of as much as possible. But when you do branching, um, the progression of the system works better when you actually account for a fact that a branch took place. So if we go back to the example of a fork, if I just sort of ignore that fork block existed, I am discounting sort of the weight of the path which originated that fork, right? So what you want to do in these systems is you actually want to, when there is a branch to some sort of depth, weigh in the paths that have branches more heavily than the paths that don't. So even though we didn't end up executing along those because they sort of took place in that path, the one that has greater branching is more important from the sort of weighting and system execution standpoint.
What do you mean by greater branching?
So if you think about a fork block, that's like a branch. So let's say I had like sort of two sort of chains that split, and they were both, say, 4 blocks deep from their common parent. But this one sort of had two extra uncles on it. Then it had a secondary fork, right? Than the one over here. The one that has more blocks on it, even though they're branching, is technically one that's telling me that the hash rate in aggregate in this system believes this to be more of the canonical system than this one. So in the branching, we actually want to sort of embody sort of the number of branches and convergences that take place as part of the weight.
So here's an interesting point of view there, which is, branching in our view of physics, sort of branching is the story of branchial space, the story of different paths of history, the story of quantum mechanics, and so on. And what you're effectively saying there, I think, is that normally we imagine that definite things happen. So we humans don't want to follow multiple paths of history. But actually, one of the things that's come out of our physics project is that humans actually do, to a small extent, follow multiple paths of history. So it's just like saying we're observing molecules in a gas or something. We don't observe individual molecules. We aggregate over large numbers of molecules. We're averaging over regions of space. So one of the things that we think about in quantum mechanics is we're averaging over regions in branchial space. We're averaging over multiple branches in this multi-way graph. So in other words, it's not the case that we only have to consider, in a sense, one branch. And what you're saying, which is interesting to me, is that in your blockchain setup, it is also the case that you have to think about branchial space. You have to think about what happens on different branches. It's not just you live one branch and that's all there is to the universe, so to speak. It matters the things that, just like my view of quantum mechanics these days is that there is, our view of reality is the result of aggregating a bunch of different branches, not an infinite number of branches. In fact, the indeterminism of quantum mechanics, and by the way, I think the same thing is true of your system. So imagine you have the absolutely whole graph, the full multi-way graph. In our case, it might be the full Ruad. You've got every possible thing that can happen. Okay? Then my claim about quantum mechanics is the reason that quantum mechanics seems to have randomness is that we live at a particular place in branchial space. So if we were to scan across all of branchial space, we'd see every possibility. But we are at a particular place in branchial space. So it's the same thing in physical space. the laws of physics might be the same, but the details of the night sky are specific to us being on this particular planet. And it's not the case that there's no theory that says why we're on this planet rather than another planet. It's just we happen to be on this planet. But an important feature is we're all on the same planet. So we all see the same night sky. The night sky is in some sense random relative to what it could be in different places in the universe, but yet all humans kind of agree on what the night sky looks like.
Well, that's interesting, right? So in the case of the blockchain, if you're separated in space on the planet, you could find yourself in one of the different branches, which would mean that you see a different view of reality until enough hash rate goes to reconverge reality. So you would see sort of the same phenomena, and that
I mean, right,
yeah.
and it's this. Okay, so I think it's tricky because in the case of let's say there are folks living on Mars, there are folks on Earth, and they've lived separately, and they've got completely different time systems, and then they finally meet, and they say we better coordinate our time. That's an example of one of these sort of convergence events where you start having to sort of get to a single uniform result. But I think the place I was going with which I think has an analogy in blockchain potentially with Branchial space and quantum mechanics is this question of why did the dice roll the way they rolled in a particular quantum experiment? Well, they rolled that way because we happen to be in this place in Branchial space and not another one. But one of the remarkable things about quantum mechanics is that we all think the definite thing happened. We all think the dice rolled that way. And my claim is the reason that we think that is because we all happen to be in a very small region of Branchial space together. We're all in this kind of flock in Branchial space. And just like we're all on this one planet, if we were able to be somewhere else in Branchial space, then we would have a different view of what happened. Then the dice would roll differently. But because we are together, it's because we as observers are sort of localized in Branchial space that we believe we have a common reality, so to speak.
Yeah.
Now, interesting question. What's the analogy of that in the blockchain? But I want to say that I think that there is the Uber blockchain, so to speak, the Ruad of blockchains, which is the kind of the ultimate multi-way graph of every possible block that could be produced. Okay, and there is some, and when you actually mine out the blockchain, you're exploring a tiny fraction of all those possibilities. And so then the question would be, which I'm trying to think through the answer, that exploration, it's funny because unlike physical space and probably well, okay. So in the physics case, I bet there's an analogy here, but in the physics case, the reason that we are all sort of consistent in the way that we observe physical space is because it takes a lot of effort to zoom to the other side of the universe. One feature of us that I think is more significant than we might give credence, that we might imagine, is that we have mass, which means we just sit here. If we were photons, we never get to sit here. We're all zipping around the universe. No time is passing for us, and we're zipping around the universe. But we have mass, we have non-zero mass, which means that we can sit in one place. And that's why, in effect, this sort of flock of observers is sort of consistently sitting in this one place and doesn't get to zoom to the other side of the universe. Now, exactly what the analogy of that, I think there is an analogy to that in Branchial space. I don't fully understand it yet. I think that the mass in physical space is actually the same mass in Branchial space. And the analogy of kind of in physical space, to go somewhere else, you have to have a great big rocket to push you there. Exactly how that works in Branchial space, I don't yet know. I think it has a lot to do with virtual particles and particle physics, but I don't yet know how it works. But so in your case, in blockchain, there's sort of the question of, okay, the miners are mining out this part of branchial space in blockchain space. Now another miner is, it seems, maybe, as if, but I don't think it really works. No, it isn't going to work this way. And I think I understand why. So you might imagine that two different miners would just be randomly arranged in different places in branchial space, in blockchain branchial space. And that therefore they could be completely uncorrelated in what they're doing. My guess is the reason it doesn't happen that way is because the miners each one is trying to continue a blockchain. Each one is trying to, and so just like you talked about forks, the local forks in the blockchain, it is the case that two miners could end up with two different forks, but those miners are still very close together in blockchain branchial space because they only forked recently. If they had allowed themselves to fork completely long ago, they could be in very different places. But because I think the way one needs to think about it is it's not just the latest hash that the miners found, it's the whole sequence of hashes the miners believed in. That's what's relevant to sort of where the miners are in blockchain branchial space.
Yeah, no, that's a fair statement. So like in the sort of information theory of this, right, we try to measure the property of safety, which has to do with finality, meaning in a proof of work blockchain, your sort of security that your transaction has happened and will get reversed is really an economic guarantee. There's two steps of the process. One is a statistical finality, and then one is sort of economic finality. Statistical finality comes when you've sort of taken enough samples of the hash rate via blocks out of the system to know that it sort of represents the majority of hash. And then economic finality comes when you effectively, for the amount that you're sending, there's been enough work done such that if there were a strictly sort of Byzantine motivated attacker, they couldn't profitably sort of private mine a chain and revert your transaction. Um, so those are sort of like the two concepts of finality. So there's very much in this system the concepts of sort of requiring greater degrees of sort of certainty about um, sort of shared understandings of history at some depth, right? So you go sort of 10 blocks back in the sequence, we all need to probably be on the same page, else these sort of blockchain systems don't work well. So the further back you go, sort of the higher guarantee you need to have that everyone's indeed aligned. So you indeed are correct that at some point, if the branch was very deep, effectively you would end up in two permanently forked settings, which would never reconverge. So there is an analogy there for sure.
No, I think what's happening is that your miners effectively are being forced to live nearby in blockchain branchial space. Now, by the way, the Byzantine attack reminds me a lot of Maxwell's demons. I mean, in other words, I'm imagining the Byzantine Maxwell's demons because what they're trying to do is somehow they're trying to beat, they're trying to beat the inevitable sequence of they're trying to untangle the web that's been created by this sequence of kind of transactions and consensus determinations and so on. So they're trying to out reverse engineer that. It's kind of like an army of Maxwell's demons attacking this kind of entropy in the system, so to speak.
Yeah, no, I could see that. I have one question for you that's fascinating. I mean, I couldn't really find an answer. When you originally started sort of talking about branchial space, you more often than not referred to it as branchial space, and you referred to it as, trying to figure out sort of like the rule that or set of rules that sort of led to the outcomes that would give us the sort of physics that we observe through our reductionist theories. And at some point, you moved to this concept of a Ruad, where you were basically saying that the rule is all rules, which in an information science standpoint, I would say is a Turing complete system, uh, potentially.
It's a completion of a Turing complete system in some sense. It's the all possible Turing complete systems. But
Right.
yes, the
But I guess my question is I'm just wondering, there was an intuitive leap that I didn't fully understand in that process to say, there's obviously good justification to say, why would any singular rule sort of be the special rule that the universe would choose to follow? That's sort of like a fair statement. Therefore, any number of rules could be the possibility, but then to go from that to not just saying it's a subset to saying it's all possible rules, um, I guess I missed that intuitive leap that it's all possible rules. And if it is all possible rules, and we are talking about something that's Turing complete, there could arguably be then a reduced representation that is the de minimis set of things that is needed to create that sort of Turing complete set of rules, right? Just in that, right? I think all logic comes from two types of gates, right? XOR and NAND, I believe, if I recall
you
correctly.
only need NAND. NAND
Oh,
is enough.
you only need NAND. You can get it all
You
done with
only
NAND.
need NAND.
So maybe that's the universal rule. Because if we're trying to get to being Turing complete, that might be like a strong argument. But I'm just interested to hear sort of your perspective on that jump and just
Right.
understand it a little bit better.
One has to untangle several points here. Okay. So first point, sort of the historical progression. I mean, this idea of branchial space, I always, this word branchial came up when Jonathan Gorard and I were discussing the physics project. We both have British accents. And so I'm always, I realized I was sort of terrified at some point later on to think, oh my gosh, we invented a word that can only be pronounced in a British accent, but this isn't quite true. But that was a concern. That's a risk, so to speak. It was an unexpected risk. But anyway, we're kind of this idea that that we can apply a particular rule in all possible ways is kind of the thing that leads to multi-way graphs and branchial space and so on. And then I had long wondered, I had long imagined this moment when we say we found the rule for the universe. Here it is. Okay. And I was like, that will be a really weird moment because it's like, why did we get this one and not another one? And it's like, how would you think about that? What? And then I realized most questions like that end up having an answer that is sort of an almost a self-fulfilling answer. In other words, it's, that kind of question that is almost a theological question that seems at first like an almost theological question ends up, why did we get this universe? Why is this universe the one that was created, not another one? And the thing is that the Ruliad is an end run around that question. So in other words, the Ruliad never has to ask that question. Why did we get this universe and not another one? Because the story of the Ruliad is, well, we got every universe. We got everything that is, in a sense, computationally possible is something we got. Now, the thing that's the surprise is that you can say anything given that. You might have imagined that if we say anything's goes, anything's possible, that would be a useless scientific theory because you'd never be able to say anything definite on that basis. The big surprise, which I absolutely didn't see coming, is the following idea. As you pointed out several times, the observer in a model like this is inside the system. So it is a non-trivial question. What does an observer inside a system with certain characteristics perceive about that system? And the key thing that's come out is an observer who has certain characteristics, fairly loose characteristics. They're computationally bounded. They believe they're persistent in time. Those requirements alone are sufficient to constrain what the observer perceives about the Ruliad. Now, the observer, you can ask, well, which rule is the observer seeing in the Ruliad? In the end, if what you're asking about is what does the observer perceive, it doesn't matter. The observer can have many different theories about what rule is really going on, but the thing that they perceive will always be the same. Analogy. In statistical mechanics, you can say, the air in this room, the water which has run out now in this glass, is, they're both fluids and they both obey certain equations of fluid dynamics. But it doesn't matter that one of them is made of air molecules. If this atmosphere was all, argon instead of nitrogen and oxygen, the fluid dynamics equations would be the same. Their parameters might be a little different, but the equations would be the same. And it's the same thing with Ruad and observers like us, that it doesn't matter what, given those characteristics of observers like us, there are many different slices that we could be taking as observers like us, but on all of those slices, we will perceive the same physics. And that's and by the way,
would any of the constants end up being affected by the subset of rules which we perceive?
I don't think so. Because I think what happens is, it's like, what is the speed of light? Well, the speed of light ultimately is just a conversion between the number that is the speed of light, 3 times 10 to the 8 meters per second, is more a definition of meters than it is a constant of nature, so to speak. And that's the way it works with basically all the constants in our models, is they're all
but relationally, like they don't need to have certain sort of parameters to get the outcome.
Well, constants, the constants that all the constants you think about, like speed of light, Planck's constant, and so on, these are all essentially defining units. They're not.
So they're all non-relational, is what you're saying.
Yeah, I mean, in the end, there are numbers that are features of the universe. So let me give you one. One very common one that one thinks about in particle physics is the fine structure constant, about 1/137. It's related to the strength of electromagnetic forces. Okay. Now, the question is, derive the fine structure constant. It's a number. You should be able to derive it. Okay. Here's where that starts getting tricky. You say, surely in your theory, you must be able to derive that number. Okay. Even in known theoretical physics, the fine structure constant is observer dependent. And it's the canonical observer happens to observe 1/137. Why is it observer dependent? Here's why. So in particle physics, you think about an electron, for example, but there's never really a bare electron that's just an electron. There's always an electron with a bunch of virtual photons that are being emitted, reabsorbed by the electron in very short amounts of time. That's what the uncertainty principle does for quantum field theory, is it tells you can't be certain exactly how many particles there are there. There's always a whole cloud of virtual particles around this electron. So then the question of something like what's the mass of the electron, or what's the coupling of this interaction strength, which is essentially this fine structure constant for the electron, well, it depends. If you're looking at it, if you're really kicking it incredibly hard, you're an incredibly high energy observer that's, probing the electron as a particle accelerator, highest energy particle accelerator, you'll get one result. Those virtual photons that are hanging around will behave in one way. If you're looking at it from sort of kind of a low energy, zoomed out point of view, you'll get a different result. It just so happens that in the history of experimental physics, there was one canonical observation that was made. But as you make further observations with different kinds of instruments, you will get different values of the fine structure constant. So it is a pretty tricky thing to say, people say, well, can you derive the fundamental constants? Well, actually, the fundamental constants depend on the observer that's looking at them. And so you have kind of a complicated story of, well, what observer are you assuming? And then what consequence does that have, and so on.
So there's an interesting example that maybe is more fundamental than that in some ways. Right, when you're doing your physics project and you're looking at different constructs, you have a method by which you can measure dimensions, right?
Yep.
Right, and you mentioned too that you think that one of the outcomes might be that we're not always strictly in 3 dimensions. Maybe we are,
Yep.
but somewhere in the universe, you're not always necessarily in perfectly 3 dimensions. Right. And the mechanism by which you did that seemed to be not sort of a consequence of the observer. I mean, maybe it is.
It
It
really is.
seems even dimensionality is a consequence of the observer
I think
because
so.
you were basically following the paths, if I recall correctly, and then you were saying sort of what's the distance to get to the nodes, and it was
Right.
basically just like a um
It's just math.
it
But the
was
problem,
yeah, it's just theoretical math, and like there's no dimension restriction. You could have said it was 5 dimensions using the method that you were using. You could say it was two and a
right.
half, right? Um, so that seems like it's a slightly more fundamental than that.
No, the problem is the math is a simplification. Imagine you're actually going to implement that with observers. It's much less trivial. In other words, just saying, for example, let me give an example. You want to know what's the distance from place A to place B in the universe. It's a good first approximation and the thing that we're capable of handling mathematically to say, look at the shortest path in the graph from place A to place B. But that's merely an approximation. Because if you actually wanted to know how far is it from place A to place B, you'd have to stuff a photon through the graph to go from A to B and measure how much, what the time was or whatever else. And a photon is a much more complicated thing than just measuring that single, sort of line in the graph. And by the way, this matters because if you're asking, for example, can you go faster than light? Well, if you could hack the graph, if you could pick it, the graph is a complicated sort of random thing. And it's, if you were able to pick exactly the right sort of edges to go on in the graph, you could potentially go faster than light. Let me give an analogy. In statistical mechanics, you've got all these molecules bouncing around in the room, and you ask the question, can I, if I were riding on a molecule, can I get from this place in the room to the other side of the room at the speed of sound, the maximum speed that molecules go at? Well, the answer is, in practice, I won't be able to do that because my molecule will only go a micron before it gets kicked by another molecule. And so, but if I were able to be a Maxwell's demon-like operator, and I could pick, I'm surfing this molecule now, as soon as it hits this other molecule, I'm going to surf that molecule and so on, I could potentially zip across the room at the speed of sound. And you can do the same kind of thing in the physical universe, going faster than the speed of light. Well, the problem is, the good news is you could go faster than the speed of light. The bad news is it wouldn't be you if you were doing it. So in other words, there are, at the level of individual atoms of space, you could imagine doing this kind of surfing and picking which causal edge you go on and so on. But the thing that can do that is nothing like an observer like us. To be able to do that, you have to be shredded down to the level of individual atoms of space. And that's not what we're like.
So there's potentially like an inverse to that sort of discussion, and that maybe the property of a photon is that it's always picking the edges which are shortest.
Well, okay, so think about that statement. I mean, this is something I've actually been thinking about recently. We're somewhat close to having unraveled this. And it's I think I'm still too confused to comment in a sensible way on that. But I think that roughly, okay, let me make a following comment. So in particle physics, one of the kind of big methodologies are these things called Feynman diagrams, which were invented by a person I knew pretty well, Feynman. And Feynman diagrams have these lines that represent, a particle that goes from here to there. And, you can have an electron line, you can have a photon line, and so on. And I'd always thought of Feynman diagrams as being sort of a representation of, oh, there's an electron that moves from here to there, and so on. And I realized recently that that's not the right way to think about them. The right way to think about them is as causal graphs that are simply telling you the causal relationships between interaction events. And that way of thinking about, so it looks as if, not yet figured out. This is a current project of progress made yesterday and things like this. It looks like there's sort of a way of thinking about quantum field theory in terms of causal graphs And all of these stories about causal invariance and so on will play out not in blockchains, but in quantum field theory, just for and lots of questions about but this issue. Okay, so what makes mass, for example? We're beginning to see that in it's actually kind of lovely. The it's roughly the more you interact, the more mass you have. So in other words, the sort of very pure particle, which is kind of like this very pure, just one causal edge type thing, but the very pure particle, would just be having zero mass going at the speed of light. But sort of what happens is it keeps on interacting with the background of space. And that's kind of what ends up giving it its mass. Now, by the way, that's actually not that different from the Higgs mechanism in spontaneously broken gauge theories, which are part of the standard model of particle physics. I've always thought of it kind of as a hack, that to imagine that the universe is full of this Higgs field and that particles interact with it to get their mass. But I actually think now that that's much closer to what's really going on. And so the picture of a photon there is a thing that just doesn't do many of those. It doesn't do any of those interactions. It just coasts, so to speak, without.
Or it finds the shortest path.
Well, yes, but the question of the defining what it means to be the shortest path. By the time you're in this causal graph, it is, and again, this is not well untangled, okay? But it's a question of is the photon that has lived since the beginning of the universe, since 100,000 years after the beginning of the universe, when the universe became transparent to light, or transparent to electromagnetic radiation. There's a photon that started its journey at that time. That photon is part of the cosmic microwave background, and it's led a happy life until it hits our detector now. Well, we might say it's terrible because, that thing has been around for 14 billion years and we just killed it, more or less. That seems shocking. But the thing to realize is, for that photon, no time has passed since the beginning of the universe. And I think that is, in a sense, a statement, sort of nothing computationally happened to that photon in some sense. And I think that's, again, this is not well disentangled. I'm not.
No. I mean, that's. I appreciate you exploring the stuff you are currently working on. But yeah, no, I intuitively like that does start to make sense. Just to follow up on the 3D question though, you have mentioned that you think it might not be 3D. Do you have an idea of how we could practically try to measure variances in dimensionality?
Yeah, I mean, this is one of these things where experiment meets theory, and you have to do a bunch of work to go from, there's a photon, it's propagating through a 3.01 dimensional region of space. What happens to the photon? Okay, and it's that's some extension of electromagnetic theory. Unfortunately, it requires extending the very foundational notions of geometry and calculus to be able to really say that with clarity. And so we've been, one of the big projects is what we're calling infrageometry, the attempt to build a version of geometry that's built on top of hypergraphs instead of being built on top of essentially Euclidean space, ordinary flat space. Unfortunately, before our efforts, basically zero was known about this. This is an area of mathematics that's just not been explored. And to really know what happens, you kind of have to explore that. Then you have to kind of build Maxwell's equations, where you're dealing with, when you learn calculus in school, it's kind of univariate calculus or it's multivariate calculus. We need calculus with 2.3 variables, for example, which is not something that they not only don't have a textbook for that, it's something that's literally never been looked at. So
fractal calculus.
Well, but it's actually much worse than that, because fractals already have an embedding dimension. They already have, the thing lives in an outer dimensionality, so to speak, and you're just picking points within that dimensionality. So, you make a Sierpinski triangle, drawing it in 2 dimensions, but you're picking out only some points in 2-dimensional space. This is much worse. This is the thing is intrinsically, a different number of dimensions. But the fact is, I'm about to do a project really trying to explore, are there effects that we have already seen that are signs of fractional dimensional perturbations in space? And it's kind of like the Brownian motion thing I was mentioning earlier. That had been known for 70 years before people understood what its significance was. And actually, it's an experiment I'm planning to do with some friendly LLMs, because the LLMs can read 100,000 physics papers in a more effective way than I can. And the question is there an effect somewhere out there that when you put it together thematically, you realize, gosh, that was a sign of this kind of phenomenon.
Mm-hmm.
Now,
yeah, I mean, my intuition would indicate that if this does show up, there's probably some manifestation of it in the CMB. Is like, but
I would think so.
Yeah, yeah.
So. I mean, but the question is, what do you get to measure? You get to measure the intensity, the Doppler shift, the polarization. There's a limited amount of things you can measure about the CMB.
I think it would have to be the it's that like macro structure of it would be like the consequence of dimensionality. So sort of like how dense it is and how sparse it is, and if you could define like that density and sparsity, my guess is like that would have something to do with the dimensionality that created it.
Possibly. I mean, look, the other picture of what could happen is, my kind of fantasy picture, which won't play out exactly this way because things are never this simple, is, you have some light propagating through a region of fractional dimensional space and, dimension fluctuation, and the rays of light get sort of randomized. And then you can figure out that if there was this dimension fluctuation, there would be this randomization. And if you were to apply this essentially image processing filter, you would kind of deconvolve that perturbation in the way that the rays of light propagate.
So question on that point then. And I'm not an astrophysicist or anything of the sort, but there is some phenomena where there's like twin lensing that takes place.
Yeah, gravitational lensing. That's right.
No, so, but you can actually get like a mirror, like around, so you get 2 images on the same side of whatever it's lensing around. If there was deviations in dimensionality, if you did like a fast Fourier transform, right? It's like a laser interferometer at that point in time, yeah. Right? You'd be able to tell.
That's not a bad thought. I mean, the fact is that what I'm kind of imagining is, gravitational lensing involves sort of the curvature in space kind of affecting the propagation of photons. This is another effect on the propagation of photons. But in the case of gravitational lensing, what you end up with is, images of 2 different, the same galaxy image twice, for example. Now, the thing which would be super cool if it happened that way is you have what just seems like a random bunch of pixels until you apply the right deconvolution filter, and then suddenly there's an image of a galaxy there. I mean, that would be kind of a sort of slam dunk, kind of maybe slam dunk, fairly slam dunk kind of.
That would be good evidence for it, right?
Yeah, right.
Well, and your filter would tell you at least the delta.
Yeah.
Right.
Tell you what the dimension was. Right.
Yeah.
But I think that the thing that's really nice about dimension fluctuations is they are parameter independent. You don't have to know the elementary length. But this is the question of, are there phenomena we can see in the universe that probe the elementary length, kind of space-time microscopes that probe down to the elementary length? Or do we have to look for effects which are parameter independent because the elementary length is just too small? I don't know. I mean, there are effects we've looked at in terms of black hole mergers and things where there maybe are effects that maybe you could observe in the ring down of, for example, of merged black holes, where where there's, for example, trade-offs between speed of light and the maximum entanglement speed that are important. There are a bunch of different effects. I think there's a whole nother class of effects that have to do with quantum mechanics, and where, I have never been a believer in quantum computers. I first worked on quantum computers back in the early 1980s, and I always thought, there is the parallelism of quantum mechanics, but then there is the knitting together that you need to have a definite conclusion about what the answer was from your quantum computer. And the question is, it's actually has a certain blockchain analogy to it, because it's kind of like the in a quantum computer, the consensus mechanism is non-trivial. In other words, inside the quantum computer, you've got all these threads of quantum process going on, but now you have to reach consensus to be able to say, this is the answer, this is the thing the human's going to take away from the quantum computer. And that really is never accounted for. The difficulty of that knitting process, of that reaching consensus process, the difficulty of consensus is not discussed when you think about the usual formalism of quantum mechanics. And so when you do start thinking about that, well, when you actually look at practical quantum computers, people are always saying, when you go, I shouldn't say it, but, like when you go visit a quantum computer company and you finally get to the back room and you're finally talking to the actual engineer, and it's like, well, yes, we see this noise that we can't really account for, and it's all a bit messier than the front office story type thing. I have this hope that if you really get the data on all of that kind of mysterious noise, that it's going to end up the noise as the signal, so to speak.
Yeah, well, so okay, so this is interesting. I love it. We think similarly. So my background's material science, so I have a little bit more depth here. My thought process on quantum computers is that it's also BS, really, because the issue that you get is, to make them useful, you need to have sort of a high number of entangled, qubits at once, right? And the issue you have is sort of just physically, the more you have, the more likely they are to decohere. And all of quantum computing is relying on the error rates being independent. But if you think about a physical system and what would cause a qubit to want to decohere, clearly they're sharing the same environment, and just a phonon is something that won't, specifically impact one of them and not the other. Ergo, it's ridiculous to make the statement that you think that they're going to have an independent error rate just on that statement alone. So until you can prove that you can get an independent error rate, you must, I would say, assume that it would not be an independent error rate. And if it's not independent, you're going to end up converging to your statement, which is that you're just going to end up effectively measuring the noise. So
yeah, I mean, I think that I have this hope. Okay, so in our view of quantum mechanics, the superposition of possible states is a story of different branches in the multi-way graph. And what you're doing when you have a superposition is you're sampling a region of branchial space, and a non-zero size region of branchial space. You're going across multiple branches. And then there is this notion of maximum entanglement speed. Some event happens, and then that event can steadily spread out in branchial space. The event can affect other one branch can affect many branches, for example. And then the question is, what I have this guess that the maximum entanglement speed, which is the rate at which an event in branchial space can spread over time, that maximum entanglement speed is related to the noise floor, and that roughly and again, this is not properly worked out, but it's my analogy I keep on using is, imagine that you were trying to do optics. You didn't know about diffraction. You only knew about geometrical optics, and you're trying to make this incredibly good telescope. And you're convinced, you've told your investors, we're going to be able to see grains of sand on the moon, and we just have to polish the mirrors well enough to make that happen. Okay. You keep doing it, you keep polishing the mirrors, you keep saying, well, something happened, this, the thermal expansion was wrong, et cetera, et cetera, et cetera. But in the end, what is going to, screw you is diffraction, and which
Yep.
is a completely different physical phenomenon that just wasn't part of what you were thinking about. And my guess is that essentially the finiteness of the maximum entanglement speed, which is the maximum rate at which you can kind of knit together the branches of history. There's a maximum rate at which you can knit together the branches of history, and that maximum rate is what's going to determine kind of how many branches of history you can measure in a certain period of time. So if you say, I'm going to make my quantum computer, it's going to run at a gigahertz or something, and then you say, well, okay, how much can I gobble in at in a nanosecond or something, or microsecond or whatever it is, then it's going to end up, it's only a certain number of branches of history, roughly, and that is going to essentially limit your computation rate. And in the end, it's going to be a very subtle question whether you can actually do better with that kind of parallel inside, knitted together on the outside system versus a thing that's just, one thread within the system itself, one. And even then, you can have obviously multi-threaded computation where you're literally just doing different computations at different places in physical space. Forget all this Branchial space stuff.
So that's actually interesting. With Quai, right? There is a similar thing that exists. Right. So we have this hierarchy of blockchains, and each one of the zones is a shard, and the shard is asynchronously, processing transactions and doing computation. And the system ends up, as you add more zone chains, poem itself is fine, because I can effectively have an infinite number of zones, and I'm still not going to end up getting hash collisions, and therefore I can resolve consensus even with uh, effectively an infinite number of leaders. I can always sort of define the leader. Um, the thing that ends up happening though is because you have these propagation delays, because we're putting this on a physical networked construct. As I'm adding more zones, the zones still need to be practical, have these dominant references happen periodically. And the more zones that I add, the less frequent each zone gets a reference. So I can
What
add.
is a reference? A reference is your higher level blocks.
Yeah, that's right. So for example, if I have two zones under one region, right, I can make every other sort of so it would be like every fourth zone block in expectation be a region block for each one of the zones, right? So then that sort of defines the time that it would take for me to transmit state from one zone to another, right? If I were then to make that like 8 zones, to allow sort of like the correct sort of slotting and sort of propagation in the larger set, I would have to sort of keep increasing that proportionally. So instead of being like one every 4, I would potentially have to go to one every like 16 or 32, right? And then you have the next layer, which is the prime, and the prime is saying, I need to weave the regions together and all the zones under those regions. So then I also need sort of like a factor. And that factor keeps sort of getting longer and longer as you add zones to the system. So there is sort of this like finite ultimate clock limit, which is how often sort of are the zones getting referenced into their DOMs based off the number of zones that exist. In much the same way that you're saying there's sort of like a finite time to collapse. And this is technically Branchial space. Like we're literally doing the same sort of collapse. And as we create more branches, um, the the time from the observer for that collapse to take place gets longer effectively. So if there's fewer branches, we can collapse them more quickly. If there's more branches, it takes longer to collapse. And that's actually the ultimate limit of, Quai in terms of its scale, is that when you're doing transactions, the more shards we add, the longer it takes to get final settlement. So, for example, if you do a transaction, right, Visa is kind of our design criteria of 8 seconds. You need to get a confirmation in 8 seconds. So we design a single zone to get you those 8-second confirmations. Now, I could say have 2 zones and I could spend money. I could send you money for a coffee. You would get the guarantee that that's processed in 8 seconds, but you might not receive it for 40 seconds, right? So you know that it's coming, and much like, when you get paid, you have sort of an available balance versus a pending balance. You would see that it's a pending balance, and then 40 seconds later, it would become available to you to sort of respend, right? And that's the sort of limit in our system. So if we had, say, 100 zones, sort of your worst case settlement times would be an hour. So you'd still get sort of the 8-second guarantee, but you might have to wait an hour before you could actually respend the money that you receive. Because we have a larger number of branches that are trying to collapse. So the time in which it takes to do that sort of grows.
Yeah, it's interesting. Let me think about this for a second. I mean, yeah, it's the same problem as with quantum computing, right? It's
Yeah.
the same issue. And
No,
I
no,
think
no, 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 no. Hopefully, we're not hopeless like quantum computing in some way, because if we have 100 shards, we should be doing well over 100,000 TPS. And to give comparison, when people actually pay with a Visa card right now, um, you I'm sure take credit card payments. Um, you don't get all of your money for 180 days, right? They do holdbacks for some amount of money for chargebacks, and you don't really see any of your money for 60 days. So we're taking either that 60 or 180-day window, and if we're doing 100,000 TPS, that basically means that every person in the Western world that has a cell phone is using us ubiquitously as money. We've compressed that number down 5,000 or more times to worst case be an hour. So
I think you're saved by the finiteness of humanity, so to speak. If there were an infinite number of people, you would have trouble.
we would still get in trouble. That's right.
Right.
That's right.
But there are a finite number of people, and the log of the number of people is something fairly manageable.
Yeah, that's right. That's right. So like it scales to the system that it needs to scale to. But yeah.
Very interesting. I realize I should go fairly soon here, but lots of fascinating things. Actually, this has been really interesting.
I've appreciated the conversation. I hope you have too. I know I can challenge, so I hope it's coming from a good place. Just trying
It's
to.
great. Listen, it is really fascinating to think through the analogies between kind of what we see in the physics project and what you can see sort of on the ground on blockchain systems. Really interesting, and it's really and I think it's one of these places where you kind of get the places where progress gets made are often these sort of interfaces between different fields, and this is one I've thought through a bit, but not completely. And I think I mentioned probably in our previous conversation we had a few years ago, had this project trying to understand things about what we were calling it quantum money, just to have a name for it. The of trying to understand sort of blockchain meets physics project and so on. Didn't it's really interesting to see your practical implementation of somewhat different ideas, but related ideas in Quai. And I think in I'm looking forward to trying to understand more myself about economics, and somehow this sort of this bridge between physics to blockchain. I'm kind of suspecting the path, if one is going to get to other things in economics, and we talked a bunch about economics last time, is physics to blockchain to economics, which might not be, that's in sort of the arc of the history of science, that's sort of an interesting direction, a bit like the strange arc when statistical mechanics was being developed, which kind of went from kind of sort of social science to biology to physics between the studies of social systems to and people in the beginning of the 1800s to from Malthus to Darwin to Boltzmann, which is exactly the opposite of what one might have thought would happen in the history of science, so to speak, going from the physics to the kind of outlying softer sciences. It was the exact opposite in actual historical reality, so to speak. So it's fascinating to see these interplays, and it's also something where the getting intuition from sort of the real world applications of these kinds of ideas is really, really cool. Anyway, it's
yeah, well, like I said, I mean, I've followed you since you started the physics project with it again, and that I'll remind you what the origin was. It was that insight about the speed of light, sort of necessitating a finite space.
I like that, and really that's not one that I don't think I've really internalized that one, and that's the funny thing is that after the fact, when one realizes that some paradigmatic mistake was made in science, after the fact, everybody says, it's obvious. Before the fact, it's incredibly hard to crawl out of that kind of gravity well of being pulled down by the things one already thinks are true, so to speak. And I think this is to make progress in something like physics, the kind of fundamental progress I've been trying to make, it's kind of a crazy business, because you kind of have to sort of not care that you are sort of throwing away lots of things that you've long believed were true. And I think that's been, I've been lucky enough in the sort of trajectory of how the physics project came to happen, that I was sort of at a stage of life and a sort of, I knew stuff, but I didn't have a vested interest in kind of preserve every aspect of what we already know, so to speak. And so that's kind of a rare situation to be in, and that's what kind of makes this kind of thing possible. I think I'm about to turn into a croaking frog here because I've run out of water, and that's probably a sign that it's time for us to wrap up.
Wrap it up. Awesome. Well, I appreciate it. We can end it there. Hopefully we can have some more of these conversations. Yeah,
That's good.
Yeah, it's great.
Where remind me, you're physically in Austin, Texas. Is that a true statement?
Yeah, that's right. And you're in the Northeast, is that right?
Yeah, I'm in Boston.
Yeah.
No, there was just a faint possibility that I might try and make a trip to Austin at some point in the not too distant future. So I just was.
Well, if you come down, let me know and get together, have dinner.
It'd be fun to meet.
Yeah.
Anyway, is there a Quai central gathering place, or are you distributed as distributed as an organization as you are on a blockchain, so to speak?
No, so we have an office. We have about 20 people that come. We also have, external people spread out around the world, but kind of the core of the team here is in Austin. So yeah, if you make it down, we can have it by the office, we can get some dinner.
Good. Yeah, right. So, well, anyway, look, I'm impressed at your calmness and in the face of your, peak of busyness as Quai launches, so to speak. So it's I know I've been in this I have to say I've been, like when we were launching Wolfram Alpha, I was doing some utterly irrelevant things, right? Intermingled with them. In fact, I remember the evening we were launching Wolfram Alpha, we actually finally, the whole thing was live, and there were a whole bunch of people there, including some people who really wanted to talk about physics. And so I seem to remember I spent the evening of that day when the system was actually running okay, which had been kind of a drama because we this was 2009, and I decided when we launched Wolfram Alpha, we didn't know what was going to happen. We had no idea what the traffic would be. We were provisioned for I think about 200 QPS. So we'd managed to, borrow machines to the point where we could withstand about 200 QPS. And The but we had no idea what the actual traffic would be. So the whole thing might have just toppled over. And so I thought, let's have some fun. I knew the Justin Can, who'd started this outfit called Justin.tv that later turned into Twitch. But
there you
the so I contacted Justin and said, hey, we'd like to live stream this launch. And so we did, and it was kind of, and I thought this is going to be the most boring piece of technology reality television ever. And I brought in this guy I knew from BBC who was used to sort of producing programs and so on to try and spice it up a bit. But things happened. So many things went wrong that it wasn't at all kind of it was much more kind of real reality TV. The most extreme version, we were doing this, our main colo was in Illinois, and it was in the afternoon, mid-afternoon, there's a tornado warning, and the tornado is heading right for
towards your colo.
So that was as it turned out, it deviated in about 10 minutes before impact, so to speak. But it was anyway, it was an interesting experience. But that I have to say that evening, as I recall, the drama was more or less over, and the system seemed to be running okay, and we were just seeing streams of users with I have the kinds of I got to tell two stories and then I got to go, but one of them was we decided that the fail indicator, the fail whale thing, we would make be a HAL, I'm sorry, Dave, I can't do that type
Yeah.
thing. Okay. So, we're seeing the stream of user comments. So one user comment was, how did you know my name was Dave? That was one that I enjoyed. Another one that came in, in the first couple of hours was we give information about cities, right? So one of them is metro area population. Maybe I don't think it was shortened to metro population, but it might have been. I think it said metro area population, and the bug report was Omsk has no metro.
Omsk.
The city of Omsk in
Okay.
Siberia has no metro. And anyway, it was an introduction to kind of real people out in the real world
Yeah.
with an alien system, so to speak.
Yeah. No, it's tough to launch stuff. I'll tell you the stuff we're doing. There's a little bit of like a difference here versus like doing sort of deployments and running infra. So we kind of learned this in our third testnet. We had like an issue where sort of all of our nodes went down at once. But the interesting thing is because it's actually a distributed system, the system itself like didn't even notice we were gone. It was basically like, oh, they can't look at the stats page, or like, oh, sort of like the wallet RPCs aren't working. But from the perspective of the nodes, everything was fine. So we just had to sort of boot our system back up and we resynced into everybody else. But what we learned from that is that with a blockchain like this, you're not just like launching software, you're actually having to incentivize and then train and then sort of deploy like this network of individuals that are sort of like managing the system. So, right, if we have a problem, right, we have like 9 mining pools and we have several thousand nodes that we somehow have to like coordinate to try to like run a patch to and sort of get that patch to work. Um, so it was just like sort of like an interesting moment in that what you realize is you're not deploying software because like it's an incentivized software system. You're really like deploying an organism, right? So like I kind of think of Quai as like a mycelium spore, and like we programmed it and we like blew it off into the world, and now it's like taken root, manifested, and is like seeking out nutrients. And it's very hard to sort of communicate with that network and make updates, but um it's a weird thing. I guess it's like the statement.
Yeah. That's the question: is have you created an alien life form that is just out on its own, being fed by some humans and kind of But it's really it's the reality, so to speak, and we are merely its attendants, so to speak.
Yeah. Yeah, right. Well, I mean, because no one controls it, right? So like it kind of gets weird, and that it is sort of the most akin form of life form of like software that at least I can think of until we actually get to AGI and they start doing their own thing. But until then, it's
Oh, I think the combination of AGI with blockchain gets kind of interesting, but
that's like another discussion we should have.
right.